Hello and welcome back. If you're here, maybe you had a long day. Maybe your mind is still spinning with thoughts that won't quite settle. Or perhaps you simply enjoy drifting off while learning something new, letting curiosity and calm exist in the same space. Whatever brought you here tonight, I'm glad you're listening. Tonight we're traveling to the bottom of the world, to a place where the sun disappears for months at a time, where ice holds secrets millions of years old, and where silence becomes so profound you can hear your own heartbeat. We're going to Antarctica, Earth's frozen archive, its climate regulator, its last true wilderness. It's a continent that asks more questions than it answers, and in that uncertainty, there's something deeply restful. Before we begin, if you enjoy these videos, a like or subscribe helps more than you might think. It tells the algorithm that contemplative science belongs here too, that not everything needs to be fast and loud. And if you have a topic you'd like me to explore in a future video, leave it in the comments. I read them all, usually late at night, when the world is as quiet as Antarctica's interior. Now let's begin. Close your eyes if you'd like. Get comfortable. And let's drift southward together, to a place where time moves differently, and ice remembers everything. Antarctica is the fifth largest continent, covering about 14 million square kilometers, roughly twice the size of Australia. But statistics like that don't quite capture what it means, do they? Imagine a landmass so vast that you could fit the United States and Mexico inside it, with room to spare. A continent where you could walk in a straight line for weeks and never encounter another human being, never see a tree, never hear anything but wind and your own footsteps on ancient ice. What makes Antarctica truly different, though, isn't just its size. It's what's missing. There are no permanent human residents, no indigenous peoples, no cities built over centuries, no borders fought over, no history of human civilization reshaping the land. It exists almost entirely outside the human story, preserved in a state that predates us by millions of years. Scientists visit, researchers winter over in the darkness, explorers test themselves against its extremes, but nobody truly lives there. Nobody calls it home in the way we call other places home. In a sense, Antarctica belongs entirely to science and ice. It's a planetary commons, a place we've collectively agreed to study rather than exploit, to wonder at rather than conquer. And there's something deeply peaceful about that, isn't there? A whole continent dedicated to understanding rather than owning. A reminder that not everything needs to be claimed, that some places can simply exist, vast and quiet, and utterly themselves. About 98% of Antarctica is covered by ice that averages 1.9 kilometers thick. Think about that for a moment. Not in abstract numbers, but in real terms. If you stood at sea level and looked up, that ice would tower above you, higher than 5 Empire State Buildings stacked on top of each other. Higher than most mountains you've ever seen, and that's just the average. In some places, the ice is over 4 kilometers deep, so thick that mountains are completely buried beneath it. Invisible ghost ranges we only discovered with radar. All that ice, nearly 30 million cubic kilometers of it, presses down on the continent with unimaginable weight. It's so heavy that it's actually pushed the bedrock beneath it down, deforming the very bones of the earth. If all that ice melted, which it won't anytime soon but could over centuries if we don't change course, global sea levels would rise by approximately 60 meters. 60 meters. That's enough to submerge most coastal cities, New York, London, Tokyo, Mumbai, all drowned under waves that Antarctica has held frozen for millions of years. But let's not dwell on catastrophe. Instead, imagine the weight of all that time compressed into ice. Each layer represents a year of snowfall, slowly compacting under its own weight, squeezing out the air until it becomes blue-white and dense as rock. At the very bottom, where pressure is greatest, ice that fell as snow 4 million years ago still exists, trapped and preserved, holding memories of an Earth we can barely imagine. That's what 98% coverage means. Nearly the entire continent wrapped in frozen time, quiet and patient and impossibly heavy. Here's something that surprises almost everyone. Antarctica is technically a desert, not metaphorically, not in some poetic sense, but by the actual scientific definition. It receives less than 50 millimeters of precipitation annually in its interior. Less than the Sahara, less than Death Valley, less than almost anywhere else on Earth. This makes it not just a desert, but the driest continent on our planet. The reason is simple, if counterintuitive. Cold air can't hold much moisture. When air is frigid enough, and Antarctic air is devastatingly cold, it becomes incapable of carrying water vapor. So even though Antarctica is surrounded by ocean, even though it sits on top of 70% of Earth's fresh water, the atmosphere above it is bone dry, unable to produce snow or rain. The precipitation that does fall is mostly tiny ice crystals that drift down from clear skies, accumulating so slowly that a single snowfall might take years to equal what falls in one winter storm elsewhere. In some valleys, the dry valleys we'll talk about later, it hasn't rained for nearly 2 million years. 2 million years of absolute drought, where the only moisture comes from occasional snowflakes that evaporate before touching ground. These places look like Mars, all rock and dust and desolation, surrounded by the largest ice sheet on Earth. It's a beautiful contradiction, isn't it? A desert of ice, the driest place on Earth completely covered in frozen water. Antarctica loves paradoxes like that. It collects them the way other deserts collect sand. The Antarctic ice sheet contains about 70% of Earth's fresh water. Let that settle for a moment. 7 out of every 10 drops of fresh water on our planet, all the water in all the lakes, all the rivers, all the glaciers, all the groundwater we pump from wells, most of it is locked in Antarctic ice. If you could somehow drink a glass of water from every freshwater source on Earth, 7 of those glasses would come from Antarctica. This matters more than it might seem at first. Fresh water is what makes life possible for terrestrial creatures like us. We can't drink seawater. The salt would kill us. We need fresh water, and most of what's available to us is a tiny fraction of Earth's total. Antarctica holds the vast reserve, the planetary savings account we didn't even know existed until relatively recently. It's been building this reservoir for millions of years, accumulating snow that compresses into ice that never melts, layering century upon century into a frozen library of water. And it's not static. Even frozen, that water is moving. The ice sheet flows like an incredibly slow river, grinding from the interior toward the coast over thousands of years. When it reaches the ocean, it either melts or calves off as icebergs, releasing fresh water back into the system. But for now, for this moment in Earth's long history, most of it stays put. a massive reserve of fresh water just sitting there at the bottom of the world, patient and cold and vital in ways we're still learning to understand. It's a reminder that sometimes the most important things are the ones doing absolutely nothing, just existing, holding something precious until it's needed. Antarctica wasn't officially sighted until 1820, making it the last continent discovered by humans. For all of recorded history, nobody knew it was there. Ancient cartographers sometimes drew a mysterious Terra Australis on their maps, a hypothetical southern land they believed must exist to balance the continents in the north. But they were guessing, imagining, hoping. They had no proof. No one had seen it. No ship had reached it. Then in 1820, 3 different expeditions claimed to have sighted Antarctica within days of each other. A Russian expedition led by Fabian Gottlieb von Bellingshausen, a British expedition with Edward Bransfield, and an American sealer named Nathaniel Palmer. All saw the continent in the same austral summer, as if Antarctica itself decided the time had come to be revealed. It's a strange coincidence, almost poetic. For thousands of years, nothing. Then suddenly, from 3 different directions, humans converge on this frozen land, and the last blank space on our map fills in. What must it have been like to be on those ships, sailing into seas where no human had ever ventured, towards something that appeared on the horizon like a vision? Endless ice cliffs rising from the ocean, white and implacable and utterly unlike anything else on Earth. No welcoming beaches, no forests, no signs of life. Just ice and more ice, stretching beyond sight. They couldn't have known what they'd found, not really. Couldn't have imagined the continent's true size, its depths, its importance to Earth's climate and history. They just saw ice and rock and turned back north, carrying with them the knowledge that yes, there is something at the bottom of the world. And it is stranger and more magnificent than anyone had dreamed. No country owns Antarctica. It's governed by the Antarctic Treaty, signed in 1959 by 12 nations, and now agreed to by 54. Think about what that means for a moment. An entire continent, larger than Europe, set aside from national ownership. No borders, no territorial disputes, no armies claiming territory in the name of kings or presidents. It's the only continent dedicated by international law to peace and science, where military activity is explicitly forbidden. This happened during the Cold War, no less. In 1959, the United States and Soviet Union were locked in bitter rivalry, building nuclear arsenals, competing in space, fighting proxy wars around the globe. Yet somehow, impossibly, they agreed that Antarctica would belong to no one and everyone. 7 countries had made territorial claims before the treaty: Argentina, Australia, Chile, France, New Zealand, Norway, and the United Kingdom. But the treaty essentially froze those claims in place. Claimant nations can maintain them, but they can't enforce them, and no new claims are permitted. What emerged instead is something remarkable: a genuine international scientific collaboration. Researchers from dozens of countries work side by side, sharing data, sharing resources, sharing the quiet wonder of living at the end of the earth. The treaty doesn't just prevent war, it actively promotes cooperation, requiring that scientific observations and results be freely exchanged. It's not perfect, of course. Questions about mining rights and resources linger. But for now, for over 6 decades, Antarctica has remained a place where science matters more than sovereignty, where understanding matters more than ownership. It's a small miracle, really, a reminder that even in our most divided moments, we can sometimes agree that certain places are too important, too precious, to carve up and claim. Some places should just be untouched and shared, belonging to everyone and no one at all. The geographic South Pole is marked by a ceremonial pole that moves about 10 meters each year. This sounds absurd at first. How can the South Pole move? It's the point where Earth's axis of rotation meets the surface, fixed at exactly 90 degrees south latitude. That should be stable, permanent, unchanging. And it is. The planet's axis hasn't moved. The South Pole as a geographic concept remains exactly where it's always been. But the ice isn't stable. The Antarctic ice sheet is constantly flowing, grinding slowly, from the continent's interior toward the coast like the world's slowest river. Ice near the South Pole moves about 10 meters per year, and the research station there, the Amundsen Scott South Pole Station, sits on top of that flowing ice. The buildings, the equipment, the marker showing where the pole is, all of it is being carried along by ice that never stops moving. So every year, on New Year's Day, researchers at the station perform a small ceremony. They relocate the ceremonial pole marker to the current position of the actual South Pole. There's also a brass marker embedded in the ice showing the previous year's position. And over time, these markers create a line showing the ice's direction of flow. It's a strange ritual, celebrating the fact that even the most seemingly permanent things are in motion. Even the bottom of the world is drifting, patient and unstoppable, carrying everything on its surface along for the ride. There's something deeply appropriate about that, isn't there? Nothing is truly still. Everything flows. Everything changes. Even solid ice at the most stable point on Earth's surface. Perhaps that's what Antarctica teaches best. That permanence is an illusion, that everything is always in motion, just sometimes too slowly for us to notice, unless we mark the years and measure carefully and pay attention. Antarctica has two ice-free areas called the dry valleys, which are among Earth's most Mars-like environments. Picture this. You're in Antarctica, surrounded by the largest ice sheet on the planet, and you come to a place where there's no ice at all, just bare rock and soil and gravel, valleys carved by ancient glaciers but now completely exposed, some of the only terrain on the continent not buried under kilometers of ice. The dry valleys exist because of the winds, katabatic winds, which we'll talk about in detail later, race down from Antarctica's central plateau at incredible speeds, sometimes exceeding 320 kilometers per hour. These winds are so powerful and so dry that they evaporate all moisture before it can freeze. Snow that drifts into the valleys sublimates directly into water vapor and disappears. Ice that tries to form evaporates. The result is a landscape that hasn't seen liquid water flow in millions of years, where some areas haven't experienced rainfall for nearly 2 million years. NASA studies the dry valleys as analogs for Mars. The conditions are similar: extreme cold, hyperaridity, high UV radiation, soils that contain perchlorates and other chemicals common on Mars. If life can survive in the dry valleys, and it can, there are microbes living in the rocks, algae growing inside stones, entire ecosystems eking out existence in one of Earth's harshest environments. Then perhaps life could survive on Mars too, or on ancient Mars, back when it had liquid water and a thicker atmosphere. Walking through the dry valleys must feel like walking on another planet. Barren, windswept, utterly, sterile-looking but secretly alive in ways you'd never notice unless you brought a microscope. It's Antarctica's reminder that life finds a way, even in the most unlikely places, even in a desert within a frozen continent at the bottom of the world, where it hasn't rained since before our species existed. Life persists, quiet, patient, waiting. The coldest temperature ever recorded on Earth was 89.2 degrees C, or 128.6 degrees, at Russia's Vostok station in 1983. Try to imagine that kind of cold. You can't, not really, unless you've experienced it. It's so far beyond normal human experience that our brains can't properly conceptualize it. Water, of course, is frozen solid, but at these temperatures, ice itself becomes strange, brittle in ways it normally isn't. At 89 degrees, exposed skin freezes in seconds, not minutes, seconds. Moisture in your breath crystallizes instantly into ice particles that fall to the ground with a sound Russians call the whisper of stars. Steel becomes brittle enough to shatter like glass. Rubber turns hard as rock. Any organic material, wood, plastic, cloth, becomes fragile and prone to cracking. Even the air feels different, thicker somehow, though that's probably just your body registering how wrong everything is at that temperature. But here's what's truly unsettling. That record from 1983 isn't even the coldest it gets. Satellite measurements have detected temperatures at East Antarctica's highest elevations, reaching 94 degrees C or 137 degrees during the polar night. At those temperatures, carbon dioxide, which normally exists as a gas, starts to freeze out of the air. You could potentially watch the atmosphere itself crystallize and fall as dry ice snow. It's a temperature that seems to belong to other worlds, to the icy moons of Jupiter or Saturn, not to Earth. Yet people work there. Scientists winter over at Vostok Station, living for months in temperatures where going outside unprotected means death in minutes. They do it to study the ice, to drill cores that reveal Earth's climate history, to understand how our planet has changed over hundreds of thousands of years. There's something admirable about that commitment to knowledge, isn't there? Enduring the coldest place on Earth just to learn what the ice remembers, just to understand what came before, so we might better predict what comes next. During Antarctic winter, the sun doesn't rise for 4 to 6 months, depending on your latitude. At the South Pole, it's exactly 6 months. The sun sets around the spring equinox and doesn't rise again until the autumn equinox. 6 months of continuous darkness, broken only by moonlight, starlight, and the occasional aurora dancing overhead. Research station crews live through this, experiencing something that's profoundly unnatural to humans. Total darkness, not for one night, but for weeks and weeks and weeks, until the darkness starts to feel normal and the concept of sunrise becomes abstract, theoretical, hard to remember. People describe the darkness differently. Some find it oppressive at first, then gradually peaceful. Others struggle with it the entire time, their circadian rhythms disrupted, their moods darkening with the sky. Most stations maintain strict light schedules indoors, trying to preserve some sense of day and night even when the world outside offers no cues. But you can't entirely escape it. You know that outside the warm, lit station, there's nothing but cold and dark and ice stretching to the horizon. But there's beauty in it too. The stars are unbelievably bright, undimmed by light pollution or atmospheric haze. The Milky Way stretches overhead like a river of light, so dense with stars that you can see your shadow by starlight alone. The aurora australis, the southern lights, puts on shows that last for hours. Curtains of green and red and purple shimmering across the sky, silent and vast. And when the moon is full, it circles the horizon for days without setting, casting silver light across the ice that makes the whole landscape glow. Some winter overcrews say the return of the sun is the most emotional experience of their lives. After months of darkness, that first sliver of gold on the horizon, it's overwhelming. People cry, cheer, stand in silence, watching the light strengthen. It's a reminder of how much we take for granted, how our whole existence is built around a star we barely think about until it's gone. Antarctica teaches that lesson thoroughly. In 6 months of darkness, that makes sunrise feel like a miracle all over again. Antarctica has no time zones because all lines of longitude meet at the poles. Think about what that means. Time zones exist because Earth rotates, and we need a system to track when the sun is overhead at different locations. But at the South Pole, all directions are north. You can walk around the pole in a few minutes, crossing every time zone on Earth, technically experiencing an entire day's worth of time zones in the time it takes to drink a cup of coffee. The concept breaks down completely. So what time is it in Antarctica? The answer is wonderfully arbitrary. Research stations typically use the time zone of their home country, or sometimes the time zone of the supply base that supports them. McMurdo Station, run by the United States, uses New Zealand time because their supply flights come from Christchurch. Amundsen Scott Station at the South Pole uses New Zealand time too, even though it sits at a point where time zones are meaningless. Russian stations use Moscow time. The result is a patchwork of different times across the continent. Neighboring stations sometimes separated by 8 or 10 hours on the clock, despite being geographically close. There's something almost comical about it, but also something that reveals a deeper truth. Time, as we experience it, is a human construction layered on top of physics. The sun rises and sets according to Earth's rotation, sure, but 3 p.m. is a concept we invented, an agreement we all made to coordinate our activities. At the poles, that agreement becomes visible for what it is: arbitrary, necessary, entirely made up. Antarctica exists outside the system, a place where you could celebrate New Year's Eve multiple times by walking between stations, where the question, "What time is it?" has no natural answer. Only the answer we choose to give it. Mount Erebus, Antarctica's most active volcano, has a permanent lava lake in its crater. Imagine that for a moment, at the bottom of the world, in temperatures that regularly drop below 40 degrees C, there's a mountain with a lake of molten rock bubbling at around 1,000 degrees. It's the southernmost active volcano on Earth, a place where fire and ice coexist in the most dramatic way possible. The lava lake has been active for decades, possibly centuries. We don't know exactly how long because humans only discovered it in 1972, when volcanologists first peered into Erebus's summit crater and saw the glowing red lake below. It's one of only a handful of permanent lava lakes in the world. Most volcanic eruptions are episodic, explosive, temporary. But Erebus just keeps burning, day after day, year after year, a pool of molten rock exposed to the atmosphere and completely indifferent to the frozen landscape surrounding it. The volcano is named after HMS Erebus, one of the ships used by James Clark Ross's 1841 expedition to Antarctica. They named the volcano after their ship, which itself was named after Erebus, the Greek primordial deity of darkness. There's something fitting about that, a dark god's name given to a mountain of fire burning in perpetual twilight, surrounded by ice that never melts, despite the heat burning at the summit. Scientists study Mount Erebus to understand volcanic processes, to learn how lava lakes work, to explore the unique ecosystem of microbes that live in ice caves warmed by volcanic heat. Because of course there are microbes there, living in impossible conditions, thriving in the space between fire and ice where nothing should survive. Antarctica specializes in these contradictions. Deserts of ice, darkness lit by stars, frozen mountains breathing fire. It's a continent that refuses to make sense in ordinary ways. Antarctica is the highest continent on Earth, with an average elevation of about 2,500 meters. That's higher than any other continent's average, higher even than famously mountainous regions. If you stood at a random spot in Antarctica and compared it to a random spot on any other continent, you'd almost certainly be higher. But this isn't because Antarctica is particularly mountainous, at least not entirely. It's because of the ice. The ice sheet adds tremendous height. In many places, the bedrock beneath is actually at or below sea level. The land itself isn't particularly elevated, but stack 2 kilometers of ice on top of that bedrock, and suddenly you're standing at altitudes where the air is noticeably thin, where altitude sickness becomes a genuine concern for people who fly into inland stations. The South Pole sits at an elevation of about 2,135 meters, and most of that elevation is ice. You're standing on frozen water piled so deep that it reaches higher than most mountains. There's something surreal about that. You're at sea level, in a sense. The rock beneath your feet is near oceanic elevation, but you're also at high altitude, breathing thin air, experiencing the effects of elevation. The ice has built a second continent on top of the first, a nation of frozen water with its own topography, its own valleys and peaks and plateaus, and it's constantly changing, flowing, shifting, building up here and melting there, creating a landscape that exists in multiple dimensions at once. The continent beneath the ice, ancient and rocky and relatively stable, and the continent of ice on top, young in geological terms, and dynamic and utterly transformative. If the ice melted, which again, it won't do quickly, but could over centuries, Antarctica's average elevation would drop dramatically. Some areas would be underwater, flooded by the surrounding ocean. Others would slowly rise as the bedrock rebounds from the weight of ice that's been pressing down on it for millions of years. The continent would reshape itself, revealing mountain ranges we've never seen, valleys that have been hidden since before our species existed. It would be, in effect, a new continent emerging from beneath an old one. But for now, Antarctica remains the highest, its elevation built from water that fell as snow long before anyone was there to see it, accumulating layer by layer into a frozen tower at the bottom of the world. The Antarctic convergence is an invisible boundary where cold Antarctic waters meet warmer northern waters. It's not a line you can see exactly. There's no color change that's obvious from a ship's deck, no dramatic shift in wave patterns, but cross it, and you can feel the difference. The air temperature drops, the ocean temperature drops. The quality of light seems to change, becoming sharper, clearer, more crisp. This convergence happens because cold water is denser than warm water, so Antarctic water sinks as it flows north, sliding beneath the warmer water from temperate latitudes. The boundary where they meet circles the entire continent, roughly following the 50th parallel in most places, but wandering north and south depending on currents and seasons. It's one of the planet's major oceanographic features, a mixing zone where different marine ecosystems collide and interact. Cross south of the Antarctic convergence, and you're in a different world. Different species of plankton, different fish, different birds. The wandering albatross, which spends most of its life riding winds around the Southern Ocean, tends to stay south of the convergence. Fur seals and elephant seals hunt in the cold, nutrient-rich waters south of the boundary. The convergence acts like an ecological fence, not absolute but significant, separating the Antarctic marine ecosystem from the rest of the world's oceans. Sailors have known about this boundary for centuries, even before they understood the science. They could feel the change, see it in the different birds that appeared, sense it in the way the sea's character shifted. Now we understand it as part of the Antarctic circumpolar current system, the massive flow of water that circles the continent and helps regulate global climate. But understanding the science doesn't diminish the experience of crossing it, that moment when the ocean changes character, when you truly enter Antarctic waters. It still feels significant, a threshold crossed, a boundary passed into a realm that plays by different rules. There are no polar bears in Antarctica. They live only in the Arctic, at Earth's opposite end. This surprises people sometimes because we tend to lump polar regions together in our minds. Ice, penguins, polar bears, all mixed up in a vague polar category. But the Arctic and Antarctic are fundamentally different, separated not just by distance, but by millions of years of evolutionary isolation. Polar bears evolved in the Arctic relatively recently, maybe 150,000 years ago, from brown bears that adapted to sea ice environments. They're specialized for hunting seals at breathing holes, for swimming in icy water, for surviving on a landscape of floating ice. Antarctica has seals too, plenty of them, and ice aplenty. In theory, polar bears could probably survive there if we transported some. But we haven't, and we shouldn't, because Antarctica's ecosystem evolved without any large terrestrial predators. The seals there are naive, unfamiliar with land-based threats. Penguins walk around with no fear of anything except leopard seals and orcas in the water. Introducing polar bears would be catastrophic. The two polar regions have been separated for millions of years, long enough for completely different ecosystems to evolve. The Arctic has polar bears, Arctic foxes, reindeer, musk oxen, a whole suite of land mammals. Antarctica has none of those. Its largest purely terrestrial animal is a wingless midge less than a centimeter long. Everything else is tied to the ocean. Seals, whales, penguins, all marine or marine dependent. It's a reminder that similar environments don't necessarily produce similar life. Isolation matters. History matters. Evolution follows different paths even when the destinations seem alike. There's also something symbolically appropriate about polar bears being absent from Antarctica. It preserves the continent's character as a place uniquely devoted to ice and ocean and birds and science. No large predators prowling the ice sheets. No land mammals competing for territory. Just the creatures that belong there, that evolved there or migrated there by sea and air, existing in an ecosystem that's harsh but balanced in its own particular way. Antarctica doesn't need polar bears. It's complete as it is, strange and specialized and utterly itself. Emperor penguins never touch land. They breed, raise chicks, and live their entire lives on Antarctic sea ice. Think about what that means. These birds, the largest penguins in the world, standing over a meter tall and weighing up to 40 kilograms, spend their entire existence on frozen ocean. They never walk on solid ground, never nest on rock or soil, never experience what land-based life is like. The ice forms in winter, thick and stable enough to support breeding colonies, and that's where emperors make their home. Their breeding cycle is extraordinary. They gather in colonies in March or April, as Antarctic winter approaches and most other life is fleeing north. The females lay a single egg, then transfer it to the males and immediately leave for the ocean to feed. The males stay behind, each balancing an egg on his feet, tucked under a fold of skin to keep it warm in temperatures that drop to 40 degrees or colder. They huddle together in groups of thousands, rotating positions so that everyone gets time in the warm center and time on the cold edge. They don't eat for months, living on stored body fat, losing up to half their body weight while incubating eggs in the harshest winter on Earth. When the chicks hatch, the females return, having spent months at sea feeding and building up reserves. They regurgitate food for the chicks, and now the males finally get to leave, walking sometimes hundreds of kilometers across ice to reach the ocean and eat for the first time in 4 months. The chicks grow through winter, huddling together in creches while parents take turns foraging. By summer, when the sea ice begins to break up, the chicks are large enough to fledge, and the cycle starts over. But here's the fragile part. Emperor penguins depend entirely on sea ice timing. The ice needs to form early enough and stay stable long enough for the breeding cycle to complete. If the ice forms too late or breaks up too early, entire colonies can fail. As climate warms and sea ice patterns change, emperor penguins are being forced to adapt. Some colonies have disappeared. Others have relocated to new areas where ice conditions are more favorable. It's a species perfectly adapted to one specific set of conditions, and those conditions are changing faster than emperors can evolve. They're ice specialists in a world where ice is becoming unreliable, living their entire lives on a platform that might not be there for their grandchildren. Antarctic krill, tiny shrimp-like creatures, have a total biomass greater than all humans on Earth combined. Estimates suggest around 500 million tons of krill swarm in Antarctic waters, forming dense clouds that turn the ocean pink and form the foundation of the entire southern ocean food web. These creatures, each one only about 6 centimeters long, collectively outweigh our entire species. Let that sink in for a moment. All 7 billion humans, with all our cities and agriculture and industry, we're smaller, as a biological mass, than a swarm of tiny crustaceans living in the coldest ocean on Earth. Krill feed on phytoplankton, microscopic algae that bloom in Antarctic waters when sunlight returns in spring. The krill swarm in enormous numbers, filtering the water for these tiny plants, and in turn become food for almost everything else. Whales eat them by the ton, filtering enormous mouthfuls of water to strain out the krill. Seals hunt them. Penguins dive for them. Fish, squid, seabirds Nearly every animal in the Antarctic ecosystem depends on krill either directly or indirectly. They're the crucial link between the sun's energy, captured by phytoplankton, and the larger animals that make Antarctica famous. But krill populations are changing. Warming waters affect their breeding. Loss of sea ice, which they depend on for shelter and food sources during winter, threatens their numbers. Commercial fishing targets krill for fish meal and omega-3 supplements, adding pressure to populations that are already stressed. If krill populations collapse, the entire Antarctic ecosystem goes with them. The whales, the seals, the penguins, all of them dependent on these tiny, swarming creatures that we barely think about. There's something humbling about krill. They're small, individually insignificant, easy to overlook. But together, they form one of the largest biomasses on Earth, supporting ecosystems that span thousands of miles. They're a reminder that importance doesn't scale with size, that the foundation of everything we find magnificent and beautiful is often small, numerous, and invisible until you look closely. Antarctica runs on krill. Remember that next time you see a penguin or think about whales. Behind every large Antarctic animal is a story that begins with millions of tiny krill, swarming in cold water, eating algae, and being eaten in turn. Weddell seals can hold their breath for over 80 minutes while diving up to 600 meters deep. 80 minutes. An hour and 20 minutes underwater, in complete darkness, hunting fish and squid in the deep ocean beneath Antarctic ice. Try holding your breath right now. Most people can manage a minute, maybe two if they're trained. These seals do it for an hour and a half, diving deep enough that the pressure should crush them, in water cold enough to kill most mammals in minutes. They've evolved extraordinary adaptations for this lifestyle. Their blood carries far more oxygen than ours, packed with hemoglobin and myoglobin that turn it almost black. Their heart rate drops during dives, slowing from 60 beats per minute to sometimes as low as 5, conserving oxygen by reducing blood flow to non-essential organs. Only the brain and heart get full oxygen delivery during deep dives. Everything else goes into a kind of suspended animation, waiting patiently for the seal to return to the surface. Weddell seals live farther south than any other mammal, often staying in areas where ice covers the ocean year-round. They maintain breathing holes by gnawing at the ice with their teeth, keeping pathways open even as the ice grows thicker through winter. You can hear them underwater, clicking and trilling and making sounds like science fiction spaceships, echolocating to navigate in absolute darkness. They hunt by sound in an alien underwater world where light never penetrates, where the only warmth is their own bodies, where pressure increases with every meter they descend. When they surface, they look almost comically peaceful, lounging on ice, seemingly lazy and content. But beneath that calm exterior is a diving machine optimized for survival in one of Earth's harshest environments. They're hunting in places we could never survive, doing things our bodies could never accomplish, living a life split between ice and the deep ocean beneath it. And they make it look easy, these seals, breathing normally on the surface as if an 80-minute dive to crushing depths in freezing darkness is the most natural thing in the world. Antarctica is home to the only insect that's completely flightless, the Antarctic midge. At just 6 millimeters long, about the size of a sesame seed, it's the continent's largest purely terrestrial animal. Everything else either lives in the ocean or spends significant time there. This tiny wingless fly represents the absolute limit of insect adaptation to cold, the furthest south any insect can survive year-round. The Antarctic midge, Belgica antarctica, lives on the Antarctic Peninsula and nearby islands, in places where summer temperatures occasionally creep above freezing. It spends most of its life as a larva, living for 2 years in that stage, freezing solid in winter and thawing in summer. The larvae can survive being frozen down to about 15 degrees C, their bodies producing antifreeze compounds that prevent ice crystals from destroying their cells. They can also survive complete dehydration, losing most of their body water, and entering a state called anhydrobiosis, essentially becoming dormant seeds waiting for conditions to improve. After 2 years, the larvae pupate and emerge as adults. But the adult stage lasts only about 10 days. 10 days to mate and lay eggs, and then they die. They don't even have functional mouth parts as adults. They can't eat. They just mate, reproduce, and die, having spent 99% of their lives as larvae, waiting for that brief reproductive window. There's something both inspiring and sobering about the Antarctic midge. Inspiring because it represents the absolute limit of what insect life can endure. The coldest, driest, most hostile environment any insect has successfully colonized. Sobering because this is it. This is as good as it gets for terrestrial animals in Antarctica. A 6-millimeter flightless fly that spends most of its life frozen or dormant, living for days as an adult. The continent's entire terrestrial ecosystem consists of this midge, some springtails, mites, nematodes, and microscopic life. That's all. The ice and cold have excluded everything else, leaving only the smallest, hardiest, most patient creatures to persist on land. Some Antarctic fish have antifreeze proteins in their blood that prevent ice crystals from forming. This sounds like science fiction, but it's real, evolved biochemistry that allows fish to survive in water that should kill them. The southern ocean around Antarctica reaches temperatures below 2 degrees C in winter, which is below the freezing point of normal fish blood. Without protection, ice crystals would form in their bloodstream, growing until they killed the fish. But Antarctic fish, particularly the ice fish and notothenoids, produce glycoproteins that bind to tiny ice crystals and prevent them from growing. These proteins work through a clever mechanism. They don't prevent ice from forming entirely. That would require lowering the freezing point by several degrees, which would mean carrying impossibly concentrated solutions of antifreeze. Instead, the proteins allow tiny ice crystals to form, then coat them, preventing them from growing larger. The crystals stay microscopic, harmless, unable to damage cells. The fish swim through below freezing water with tiny ice seeds floating in their blood, kept in check by molecular guardians that evolved over millions of years. Some Antarctic fish have taken this even further. Certain species of ice fish have lost their red blood cells entirely. They have no hemoglobin, the protein that normally carries oxygen. Their blood is transparent or pale yellow. They absorb oxygen directly into their plasma and distribute it through their bodies without red cells. This works only because Antarctic water is so cold and oxygen-rich that dissolved oxygen alone is sufficient. These fish would die in warmer water. Their adaptation is so extreme that they're locked into cold environments forever. There's something beautiful about adaptation. this specific. These fish can't leave Antarctic waters. They've committed evolutionarily to one particular environment, developing solutions so specialized that they work nowhere else. It's the opposite of the generalist strategy that humans use. We adapt culturally. We build tools. We survive anywhere by changing our behavior. These fish adapted physiologically, chemically, becoming masters of one environment at the cost of being forever bound to it. They're ice specialists swimming in liquid water, their blood mixed with molecular antifreeze, living proof that evolution finds solutions we'd never imagine. Snow petrels are one of only 3 birds that breed exclusively on the Antarctic continent. They're pure white, perfectly adapted to blend with ice and snow, and can fly in blizzards that would ground any other bird. When you see one against blue sky, it's like watching a piece of cloud break free and take flight. No contrast, no shadow, just white on white, visible only when it moves. These birds are extraordinary flyers. They can navigate in winds exceeding 100 kilometers per hour, using the gales that sweep across Antarctica as highways, riding currents that would batter other birds from the sky. They nest on cliff faces and rocky outcrops, usually near the coast, but sometimes hundreds of kilometers inland, wherever they can find bare rock exposed through the ice. The nests are simple, just a scrape in stone, maybe lined with a few pebbles. But they return to the same sites year after year, sometimes for decades, building up layers of guano that mark territories used for generations. Snow petrels feed on fish, krill, and squid, diving into the frigid southern ocean to catch prey. They can drink seawater, processing the salt through special glands and excreting it as concentrated brine. This means they never need fresh water. They live their entire lives in an environment of salt water and ice, completely independent of the liquid fresh water that most birds require. They're supremely adapted to Antarctica's extremes, designed for a world of ice and wind and cold ocean. Watching snow petrels fly in a storm is mesmerizing. They seem weightless, effortless, dancing in winds that would knock a person over. The blizzard doesn't hinder them. If anything, they use it, playing in the updrafts, wheeling and diving with what looks almost like joy. Perhaps that's projection, imagining emotion in birds just trying to survive. But there's something in the way they fly that suggests more than mere survival, a mastery of their element, a belonging so complete that the worst storm Antarctica can throw at them becomes just another day, just another flight, just another dance with the wind. Leopard seals, Antarctica's apex predator, have spots that resemble a leopard's coat and teeth as sharp as their namesake. They're solitary hunters, sleek and powerful, patrolling ice edges with a kind of patient menace. While Weddell seals look gentle, almost friendly, leopard seals look exactly like what they are. Predators built for speed and violence, capable of explosive bursts of power that end with penguins or other seals dead in their jaws. They're large. Females can reach 3.5 meters long and weigh over 500 kilograms, significantly bigger than males. Their heads are disproportionately large, almost reptilian, with a mouthful of interlocking teeth designed for different purposes. The front teeth are sharp for gripping prey. The molars are specialized for straining krill from water, making leopard seals one of the few animals that can efficiently hunt both large prey and tiny crustaceans. They're flexible predators, switching between food sources depending on availability, and opportunity. Leopard seals are famous for hunting penguins at ice edges. They lurk beneath the surface, invisible in dark water, waiting for penguins to jump in. When one does, the seal strikes. Fast, brutal, efficient. But here's the disturbing part. Leopard seals don't just kill penguins and eat them. They thrash them against the water's surface, skinning them, beating them until the penguin's body separates from its skin. Then they eat the body and discard the skin, which floats away like a wetsuit someone removed and abandoned. It's graphic, violent, the kind of predation that reminds you nature isn't gentle. But they're not monsters. They're animals doing what they evolved to do, hunting in one of the most competitive environments on Earth. And occasionally, leopard seals display behavior that's harder to categorize. There are documented cases of leopard seals approaching human divers and offering them penguins, dead penguins, freshly killed, pushed gently toward the diver's camera. Is it gift-giving? An attempt to feed what the seal perceives as an incompetent hunter? Play? We don't know. The seals just do it. This strange gesture that seems almost social, almost communicative, from an animal we usually categorize as a solitary predator. Antarctica is full of these moments, behavior that doesn't fit our categories, that suggests inner lives richer than we generally acknowledge. Orcas have developed specialized hunting techniques for Antarctic seals, creating waves to wash them off ice floes. It's coordinated, intelligent, strategic hunting that requires cooperation and learning. Orcas don't instinctively know these techniques. They develop them culturally, passing knowledge from one generation to the next through observation and teaching. The wave washing technique works like this. A group of orcas identifies a seal resting on an ice floe. They swim toward it in formation, diving just before they reach the floe, then surfacing simultaneously on one side. The coordinated motion creates a wave that rolls across the floe, washing the seal into the water where the orcas are waiting. It requires timing, cooperation, and an understanding of wave physics that suggests genuine problem solving. These aren't robots following genetic programming. They're intelligent animals working together, adapting their behavior to specific situations. Different orca populations in Antarctica have different dialects and hunting strategies, variations that persist across generations, like cultural knowledge. Some groups specialize in hunting seals. Others focus on penguins or fish. They communicate with distinct vocalizations, different enough that orcas from different populations might not fully understand each other. They're not just a species. They're multiple cultures within a species, each with their own traditions, their own knowledge, their own ways of being in the world. There's something deeply compelling about that. Intelligence arising in a form so different from ours. No hands, no tool use in the traditional sense, living in an environment we can barely survive. Yet they communicate, they teach, they remember, they strategize. They have grandmothers who live decades past reproductive age, whose role seems to be knowledge-keeping, teaching younger generations where to find food in different seasons, how to hunt different prey. It's culture, unambiguous and observable, in creatures that share no recent evolutionary history with us. Antarctica's waters hold not just animals, but societies, communities with their own histories stretching back further than our records can trace. Antarctic moss can survive being frozen for over 1,500 years and still resume growing when thawed. This was discovered through ice core research. Scientists extracted moss samples from deep within ice, samples that had been frozen since the Middle Ages, and brought them to lab conditions. The moss thawed, was given water and light, and simply started growing again, as if 15 centuries frozen solid was just an extended nap. This kind of resilience challenges our understanding of what life requires. We tend to think of life as continuous. Organisms need constant metabolism, constant maintenance, constant activity to remain alive. But Antarctic moss can shut down completely. No metabolism, no repair mechanisms working. Just frozen cells waiting in darkness for conditions to improve. And they can wait centuries, possibly longer. We don't know the upper limit because we haven't found older samples that survived intact enough to test. The mechanism involves incredibly sophisticated cellular protection. As temperatures drop, the moss cells produce protective compounds, adjust their membrane composition, and prepare for freezing. When ice forms, it forms outside the cells rather than inside them, preventing the puncturing and shredding that usually kills frozen organisms. The moss essentially goes into cryogenic suspension. Every biological process stopped, waiting. This has profound implications for astrobiology. If life on Earth can survive frozen for over a millennium and resume activity when thawed, then life on Mars, if it ever existed, might still be viable in ice deposits. Europa's subsurface ocean, Enceladus's ice shell, the permanently shadowed craters of the Moon, anywhere water ice exists might potentially harbor dormant life, waiting for conditions that might not return for thousands or millions of years. Antarctic moss offers a glimpse into how patient life can be, how thoroughly it can wait, how completely it can shut down, and still remain alive in some meaningful sense. Its frozen potential, biological possibility held in ice, proof that death and dormancy are not the same thing, even when dormancy stretches across centuries. The Antarctic toothfish, also known as Chilean sea bass, can live for up to 50 years in deep, cold waters. They're large fish, growing up to 2 meters long and weighing over 100 kilograms, moving slowly through the dark depths where temperatures hover just above freezing. Their slow growth and long lifespan are adaptations to the extreme cold. Metabolism runs slower in frigid water, so everything takes longer. Growth, maturation, aging, all of it stretched out across decades. These fish don't reach sexual maturity until they're about 10 years old. 10 years just to be ready to reproduce for the first time. Compare that to fish in tropical waters, many of which mature in months or a year. The Antarctic toothfish lives on a different time scale, patience built into its biology. It hunts other fish and squid in the deep ocean, a top predator in its environment, accumulating age and size slowly and steadily. This slow life cycle creates vulnerability. When commercial fishing discovered Antarctic toothfish in the 1980s, populations crashed within years. The fish couldn't reproduce fast enough to replace losses. Take out the big, old breeding fish, and it takes decades for the population to recover, if it recovers at all. The species became a poster child for how quickly we can damage ecosystems we barely understand, harvesting fish faster than they can possibly replenish themselves. There's an irony in the name Chilean sea bass. It's a marketing invention. The fish isn't a bass, and it lives far beyond Chile's waters. But toothfish didn't sound appetizing to restaurant diners, so the seafood industry renamed it, and suddenly people wanted to eat it. The renaming was so successful, it nearly destroyed the species. Now there are strict quotas, international agreements, efforts to prevent illegal fishing. Some populations are recovering, but it's slow because everything about Antarctic toothfish is slow, including their ability to bounce back from devastation. They're still down there, these fish, swimming in cold darkness, living their long, patient lives. 50 years or more spent in a world of pressure and cold, growing slowly, hunting slowly, existing on a timeline that makes our lives look frantic and rushed. Antarctica specializes in patience. Its life forms are lessons in endurance, in taking time, in not hurrying even when everything around them is harsh and difficult. Certain species of Antarctic sponges can live for over 10,000 years, making them among Earth's oldest living organisms. 10,000 years. Think about what that means in human terms. A sponge alive today in Antarctic waters might have been growing when humans were just beginning to develop agriculture, when the last ice age was ending, when woolly mammoths still walked the earth. It's lived through the entire span of recorded human history, and the thousands of years before that, sitting on the ocean floor, filtering water, growing so slowly that decades pass between noticeable changes. These sponges grow in the cold, dark waters around Antarctica, in depths where conditions barely change from one century to the next. The cold slows their metabolism to nearly nothing. They grow millimeters per century, sometimes less, building their bodies particle by particle, cell by cell, with patience that makes glaciers look hasty. They filter water for food, extracting tiny particles of organic matter, each one contributing infinitesimally to the sponge's growth. We know their age through growth ring analysis, similar to how we age trees. The sponge's structure contains layers that can be counted, chemical signatures that can be dated. The oldest confirmed Antarctic sponge was over 15,000 years old when sampled, older than human civilization, older than most of the trees alive today, older than anything else we've found living that isn't a colonial organism or a clone forest. What does a 10,000-year lifespan mean for an organism with no brain, no nervous system, no apparent awareness? Is there any sense in which that sponge experiences its own existence? Or is it just a biological process, a chemical reaction that happens to persist for millennia? We don't know. We can't know. But there's something profound about life, that patient, that enduring, whether or not it's conscious of itself. Antarctica's deep waters hold these ancient beings, filtering water as they've done since before pyramids, before writing, before almost anything we consider part of human history. They're quiet witnesses to time, living at a pace that makes geology look dynamic. Blue whales migrate to Antarctic waters each summer to feed on the massive krill populations. A single blue whale can consume up to 40 million krill in one day, filtering tons of seawater through baleen plates, extracting the tiny crustaceans and expelling everything else. It's eating on an almost incomprehensible scale. The largest animal that has ever lived, feeding on some of the smallest, bridging the gap between microscopic and massive in a few gulps. Blue whales can grow up to 30 meters long and weigh over 200 tons. Their hearts are the size of small cars, their blood vessels wide enough for a human to swim through. When they feed, they lunge through krill swarms with mouths open, engulfing enormous volumes of water. Their throats expand like balloons, pleated skin unfolding to accommodate water that can equal their own body weight. Then they close their mouths and push the water out through baleen plates. Long, fringed structures made of keratin that filter out the krill while letting water escape. They make this journey every year, summer in Antarctica to feed, then migration north to warmer waters to breed and give birth. The journey can be 10,000 kilometers or more, one of the longest migrations of any mammal. They eat almost nothing during the breeding season, living off fat reserves built up during Antarctic summer. The entire annual cycle revolves around those few months of abundant feeding, when Antarctic waters bloom with krill, and the whales can eat enough to sustain themselves for the rest of the year. Blue whale populations were nearly destroyed by commercial whaling in the 20th century. Before industrial whaling, there might have been 250,000 blue whales. By the 1960s, fewer than 1,000 remained. They've been protected since 1966, but recovery is slow, very slow. Blue whales reproduce slowly like Antarctic toothfish. Females have one calf every 2 or 3 years, and the calves take years to reach sexual maturity. The population grows gradually, maybe increasing by a few % each year if conditions are good. They might never return to pre-whaling numbers. We might have permanently reduced the planet's capacity to support the largest animals ever to exist, all in a few decades of hunting. But they're still here, these whales, returning to Antarctic waters every summer, lunging through krill swarms, singing songs that travel hundreds of kilometers through the ocean. The largest animals on Earth, dependent on some of the smallest, both of them needing Antarctica's cold, nutrient-rich waters to survive. It's a reminder of how connected everything is, how the health of krill populations affects whales that swim across entire oceans, how changes in Antarctic ice affect ecosystems thousands of miles away. Antarctic silverfish have transparent blood because they lack hemoglobin and red blood cells. Their blood is essentially colorless or pale yellow because it contains no oxygen-carrying pigments. This sounds impossible. How can a fish survive without the protein that carries oxygen to tissues? But in Antarctic waters, it works, because the water is so cold and oxygen-rich that dissolved oxygen alone provides enough to meet the fish's metabolic needs. The fish absorb oxygen directly through their skin and gills, and it dissolves into their blood plasma. From there, it diffuses into tissues based on concentration gradients. Simple physics, no special carrier proteins needed. This works only because their metabolism is slow, their oxygen needs low, and the water exceptionally rich in dissolved gases. Move these fish to warmer water, and they'd suffocate. Their system only functions in the extreme cold of Antarctic seas. Losing hemoglobin isn't just a quirk, it's an adaptation that brings benefits in the extreme cold. Blood without red cells is less viscous, easier to pump when temperatures are near freezing. It reduces the metabolic cost of maintaining those cells. The fish essentially simplified their system, removing components that weren't necessary in their environment and gaining efficiency in exchange. But it's also a commitment. These fish are locked into cold water forever. They can't migrate to warmer regions, can't adapt to climate change by shifting their range northward. They're Antarctic specialists, evolved for conditions that exist nowhere else. And if those conditions change too much, the fish have nowhere to go. they're transparent blooded canaries in the coal mine, indicators of ocean health in the Southern Ocean. If Antarctic silverfish populations crash, it's a sign that the cold, oxygen-rich environment they depend on is changing in fundamental ways. There's something almost alien about them. Fish with see-through blood, living in water so cold it would kill most other fish, surviving through chemistry and physics rather than biological complexity. They're proof that evolution finds solutions we'd never anticipate, that life adapts to extremes by changing the very fundamentals we assume are universal. Red blood cells seem essential. Every mammal has them. Most fish have them. It's a basic feature of vertebrate life. Except when it's not. Except in Antarctic waters, where physics makes biology unnecessary, and fish swim with clear blood flowing through their veins. Algae living inside Antarctic sea ice create a hidden underwater garden that feeds entire ecosystems. When sunlight returns after winter, the underside of sea ice blooms with life, turning the frozen ceiling green and gold. This happens because sea ice isn't solid. It's full of tiny channels and pockets where extremely salty brine remains liquid even when the surrounding water is frozen. Algae colonize these spaces, creating a three-dimensional habitat within the ice itself. The ice algae bloom in spring when increasing daylight penetrates the ice, and photosynthesis becomes possible again. The underside of ice floes becomes carpeted with algae, sometimes so thick it colors the water beneath. This ice-associated primary production is crucial for the Antarctic food web. Krill graze on the algae, scraping it from the ice's underside. Larval fish hide in the ice matrix, protected from predators while feeding on algae and small zooplankton. Amphipods, small crustaceans, live their entire lives in the ice, moving through the brine channels, feeding on algae blooms. The amount of primary production from ice algae can equal or exceed that from phytoplankton in the open water, especially early in the season before the water itself blooms. The ice becomes a substrate for life, a platform that concentrates nutrients and organisms in ways that wouldn't happen in open ocean. It's a habitat type that exists only in polar regions, only where sea ice forms reliably, only where the ice is thick enough and stable enough to support these communities. But sea ice is declining. As climate warms, less ice forms each winter, and what does form melts earlier in spring. The ice algae communities are shrinking, and with them the krill nurseries they support. This matters because krill depend on sea ice during their larval stage. Young krill hide under ice and feed on ice algae, and without sufficient sea ice, krill recruitment fails. Fewer young krill means fewer adult krill in future years, which means less food for everything that depends on them. The underwater garden is fading, melting, disappearing before we fully understood how crucial it was. South polar skuas are aggressive birds that will attack humans who come near their nests. They're one of the few animals in Antarctica that genuinely view humans as a threat worth fighting, dive-bombing anyone who ventures too close during breeding season. These aren't tentative swoops. Skuas commit, striking with feet extended, sometimes making contact with heads and shoulders, making their displeasure absolutely clear. Skuas are powerful flyers, dark brown with pale highlights, built more for aggression than elegance. They're opportunistic predators and scavengers, eating fish, krill, and carrion, but also raiding penguin colonies to steal eggs and chicks. They're not subtle about it. A skua will land near penguin nests, wait for a gap in parental attention, and rush in to grab what it can. Penguins mob them, multiple adults chasing the skua away, but skuas are persistent. They keep trying, probing for weakness, waiting for opportunities. But what they're most famous for is their migration. South polar skuas breed in Antarctica during austral summer, then migrate north for the winter. But they don't just go a little north. They fly to the Arctic, to the opposite pole, covering over 10,000 kilometers in one of the longest migrations of any bird. They spend the northern summer in the Arctic, then fly back to Antarctica for the southern summer, essentially experiencing perpetual summer by switching between poles. It's an extraordinary strategy, chasing productive seasons around the globe, living in polar daylight year-round. Why attack humans? Because from the skua's perspective, we're just another large predator approaching their nest. They're defending their eggs or chicks the same way they'd defend against a seal or another bird. They don't know we're not interested in eating skua eggs. They just know we're big, we're close, and their breeding success depends on driving away anything that might be a threat. So they dive, they strike, they make it clear that this territory is defended. And honestly, there's something admirable about that. A bird weighing maybe a kilogram, attacking a human 100 times its weight, because protecting its offspring is more important than safety. It's fierce, direct, unambiguous, the Antarctic way of doing things. Antarctica was once part of the supercontinent Gondwana, connected to South America, Africa, India, and Australia. About 180 million years ago, dinosaurs could have walked from what's now Antarctica to Africa without crossing water. The continents were fused together, a single landmass sprawling across the southern hemisphere, and Antarctica sat not at the pole, but somewhere closer to temperate latitudes, positioned where forests could grow and rain could fall, and life could flourish in ways unimaginable in its current form. Gondwana began fragmenting around 180 million years ago, pulled apart by tectonic forces that are still operating today. The breakup was slow. Continents don't separate quickly. They rift and split over millions of years, opening ocean basins centimeter by centimeter. The pace of fingernail growth stretched across geological time. South America pulled away first, then Africa, then India drifted north toward Asia, and finally Australia separated, leaving Antarctica isolated. At the bottom of the world, you can still see evidence of these connections in the rocks. Geological formations in Antarctica match formations in South America, Africa, and Australia. The same rock types, the same ages, the same fossils, forming patterns that only make sense if the continents were once joined. Mountain ranges that end abruptly at one coastline continue on another continent thousands of miles away. Coal seams, mineral deposits, ancient river valleys, all of them crossing modern oceans, connecting lands that now seem completely separate. There's something almost melancholic about it. Antarctica wasn't always alone. It was once connected, part of a community of continents, sharing ecosystems and climates with lands that are now tropical or temperate. The separation was gradual enough that life could adapt, but absolute enough that eventually Antarctica became its own world, isolated by the Southern Ocean, drifting south into colder and colder latitudes until ice claimed it entirely. The other fragments of Gondwana went on to become familiar continents, warm, inhabited, green with life. Antarctica became ice. Same origin, radically different fates, all because of where each piece happened to drift when the supercontinent broke apart. Fossils show that Antarctica was covered in temperate forests about 50 million years ago, with average temperatures around 20 degrees. Ancient tree stumps and leaf fossils reveal forests where beech trees grew and marsupials wandered under a much warmer sky. This isn't speculation, we have the evidence. The preserved remains of forests that thrived in a place now buried under kilometers of ice. The fossil sites are remarkable. Petrified wood, frozen in stone, showing growth rings that indicate seasonal variations. Leaf impressions pressed into sedimentary rock, delicate enough that you can see the vein patterns. Pollen preserved in ancient lake beds, telling us what plants grew where, what the climate was like, how the ecosystems functioned. These weren't tropical forests. Antarctica was still at high southern latitudes even 50 million years ago, but they were temperate, similar to forests in modern Tasmania or New Zealand. Cool but not freezing, wet enough for trees, mild enough for diverse plant life. What happened? Why did lush forests give way to ice? The answer involves plate tectonics, ocean currents, and atmospheric chemistry. As Australia drifted away from Antarctica, ocean currents changed. The Antarctic Circumpolar Current developed, isolating Antarctica from warmer waters to the north. Without that warm water flow, temperatures dropped. Carbon dioxide levels in the atmosphere also declined over millions of years, reducing the greenhouse effect that had kept Antarctica warm. The combination pushed the continent past a tipping point, and ice began to accumulate. The transition wasn't instant. It took millions of years for forests to retreat and ice to advance, but it was inexorable. Trees that had stood for thousands of years died as temperatures dropped and precipitation turned from rain to snow. The forests gave way to tundra, then to ice, and eventually the entire continent was covered, burying the evidence of what it had been under frozen silence. Those ancient forests are still there, beneath the ice, compressed into coal seams that we've discovered but can't practically mine. Antarctica is sitting on fossil fuel deposits formed from its own ancient vegetation, a resource protected by treaty and isolation, and the sheer impracticality of extracting it. The forests became forbidden wealth, locked beneath ice that refuses to give up its treasures. Coal deposits in Antarctica prove that dense tropical swamps existed there during the Permian period, about 300 million years ago. This was before Antarctica drifted south, when it was positioned near the equator, part of Gondwana, and blessed with the kind of climate that creates coal, warm, wet, swampy, with vegetation growing so fast that dead plant matter accumulates faster than it can decay. Coal forms from plant material buried and compressed over millions of years. The process requires specific conditions: abundant plant growth, waterlogged environments where decay is slow, and burial under sediment that applies pressure and heat. These conditions existed in Permian Antarctica, creating swamps where plants grew in profusion, died, accumulated in thick layers, and eventually became the black, combustible rock we call coal. Robert Falcon Scott's expedition found coal on the Beardmore Glacier in 1912, on their return journey from the South Pole. They were already doomed, low on food, battling terrible weather, racing against time and losing. But they stopped to collect rock samples, including coal with plant fossils, because the scientific value was too great to ignore. they carried those samples with them until the end. And when their bodies were found months later, the coal was still there, evidence of Antarctica's tropical past, carried by men who would never make it home. The coal deposits remain, extensive seams running through Antarctic rock, a resource that could theoretically be mined, but is protected by the Antarctic Treaty's prohibition on mineral exploitation. It's strange to think about, a frozen continent sitting on top of fossilized jungles, coal formed from plants that grew in heat and humidity beyond anything modern Antarctica has experienced for hundreds of millions of years. The continent has moved from equator to pole, carrying evidence of its journey in layers of rock and fossil fuel, a geological memory of warmth now locked beneath ice. Antarctica started freezing over around 34 million years ago when ocean currents shifted and isolated it at the South Pole. This cooling happened relatively quickly in geological terms, transforming a green continent into an ice kingdom in just a few million years. Before this transition, Antarctica was still cool. It was at high latitude even then, but ice-free, supporting forests and diverse ecosystems. After the transition, ice sheets began to grow, eventually covering nearly the entire continent in the frozen landscape we see today. The trigger was the opening of the Drake Passage between South America and Antarctica, and the Tasmanian Gateway between Australia and Antarctica. Before these openings, warm ocean currents could flow south, bringing heat to Antarctica's coastlines. But once the passages opened, the Antarctic Circumpolar Current developed, a flow of water that circles the continent from west to east, effectively cutting it off from warmer waters to the north. This oceanographic isolation, combined with declining atmospheric carbon dioxide levels, pushed Antarctica past a climatic threshold. Ice that had previously melted each summer began to persist year-round. Snowfall accumulated, building up in layers that compressed into ice. Albedo feedback kicked in. White ice reflects sunlight, cooling the surface further, allowing more ice to form. Within a few million years, Antarctica transformed from a continent with ice caps at high elevations to a continent almost entirely covered in ice. It's sobering to think about how relatively quickly the change happened. In human terms, millions of years sounds like forever. But in Earth's history, it's a transition zone, a period where the planet's climate shifted fundamentally and a whole continent changed character. Forests that had existed for tens of millions of years vanished. Ecosystems collapsed. Animal species that had evolved in Antarctic forests either went extinct or migrated to other continents as Gondwana fragments separated. What remained was ice, silence, and a new kind of ecosystem, one built around cold and ocean rather than land and forest. Antarctica became what it is now, the frozen archive, the white continent, Earth's refrigerator, shaped by ocean currents and climate feedbacks into a landscape unlike anywhere else on the planet. Dinosaur fossils discovered in Antarctica include Cryolophosaurus, a crested predator that lived about 190 million years ago, known as Elvisaurus for its pompadour-like crest. It proves that large dinosaurs thrived in polar regions during warmer eras. Cryolophosaurus was a theropod, a meat-eater, standing about 3 meters tall and stretching 6 or 7 meters long. A significant predator, hunting in forests that once covered early Jurassic Antarctica. The crest is distinctive, a bony ridge that runs across the top of its skull from eye to eye, then rises upward in a flamboyant crest. We don't know its function for certain. Maybe it was for display, attracting mates, or intimidating rivals. Maybe it helped with species recognition. Maybe it had some role in thermoregulation, though that seems less likely. What we know is that it was unique among theropods, a feature that makes Cryolophosaurus immediately recognizable, even from fragmentary fossils. Finding dinosaur fossils in Antarctica is incredibly difficult. The continent is mostly covered by ice, and the few exposed rock formations are remote, difficult to access, and available for study only during brief summer windows when weather permits fieldwork. Yet despite these challenges, paleontologists have found multiple dinosaur species, proving that Antarctica wasn't always the lifeless frozen desert it is today. It was once warm enough for dinosaurs, for forests, for ecosystems as complex and diverse as anywhere else in the Mesozoic world. Cryolophosaurus lived during a time when Antarctica was still connected to other Gondwanan continents, but positioned at high southern latitudes. This means it experienced polar light regimes, long summer days, long winter nights, even though temperatures were warm. Imagine a Jurassic forest where summer brings months of continuous daylight and winter brings months of twilight. The dinosaurs living there would have adapted to seasonal extremes of light, unlike anything experienced by dinosaurs at lower latitudes. Did they migrate? Did they have special adaptations for surviving dark winters? We don't know. The fossils are silent on these questions, offering only the fact of their existence, not the details of how they lived. The Trans-Antarctic Mountains divide the continent into East and West Antarctica, stretching over 3,500 kilometers. This range is one of the longest mountain chains on Earth, yet it's mostly buried under ice that hides its true scale. What we see are peaks poking through the ice sheet, nunataks, islands of rock in an ocean of ice, hinting at the massive range buried beneath. The Trans-Antarctic Mountains rise from near sea level to over 4,500 meters at their highest peaks. They formed through tectonic uplift, the result of East and West Antarctica's different geological histories. East Antarctica is an ancient stable craton, a thick slab of old continental crust that's been stable for billions of years. West Antarctica is younger, more geologically active, composed of multiple crustal blocks. The boundary between them, the Transantarctic Mountains, represents a fundamental geological divide. Walking in the Transantarctic Mountains must feel like exploring a mountain range on an alien planet. The peaks are bare rock, no vegetation, no soil, just stone and ice. Glaciers flow between the peaks, pouring ice from the East Antarctic ice sheet toward the Ross Sea. The valleys are filled with moving ice, rivers of frozen water grinding through rock at a pace measured in meters per year. And everywhere, the silence. No birds in most areas, no insects, no wind-rustled vegetation, just rock and ice and sky, and perhaps the occasional distant sound of ice calving or wind howling through a coal. The mountains also contain some of Antarctica's most important fossil sites and geological records. Because they're high enough to protrude through the ice, rock formations are accessible that would otherwise be buried and unreachable. Scientists have found fossils of Glossopteris, an ancient plant that grew across Gondwana and provides evidence for continental drift. They found coal seams, dinosaur bones, and rocks that tell the story of Antarctica's transformation from green continent to frozen desert. The Trans-Antarctic Mountains are a geological library, pages of Earth's history exposed by ice and elevation, waiting for researchers brave enough to reach them and skilled enough to read what they contain. Parts of the Antarctic bedrock are below sea level, pressed down by the enormous weight of ice above. If the ice sheet melted, some areas would actually remain underwater, while others would slowly rebound upward over thousands of years. This creates a strange situation. Antarctica is both a continent and potentially a collection of islands, depending on whether you're looking at the rock surface or the ice surface. The ice sheet is unimaginably heavy. In places where it's 3 or 4 kilometers thick, the sheer weight has compressed the bedrock downward, deforming Earth's crust. The crust floats on the mantle, the semi-molten layer beneath, and the ice's weight pushes it down like a boat, settling deeper in water when you load it with cargo. Remove the ice, and the crust would slowly rise again, a process called isostatic rebound, but it takes thousands of years. The rock rises at rates measured in millimeters per year, glacially slow even by geological standards. This means that if Antarctica's ice sheet melted completely, which won't happen quickly, but could happen over centuries if warming continues, the continent wouldn't suddenly emerge as a single landmass. Much of West Antarctica would be underwater, a series of islands and straits rather than continuous land. East Antarctica would remain mostly above sea level, but even there, large areas would be flooded. The continent would reshape itself over millennia, the rock slowly rising as it adjusts to the ice's absence, coastlines shifting, geography transforming in slow motion. It's already happening in small ways. Measurements show that areas where ice loss is occurring, particularly in West Antarctica, the bedrock is rising, rebounding from reduced ice load. The process is measurable with GPS and satellite observations, millimeters per year, adding up over decades. Antarctica is breathing, in a sense, its rocky bones shifting beneath the ice, responding to changes in weight and pressure that have been building or releasing for thousands of years. It's a reminder that solid ground isn't quite as solid as it seems, that even continents flex and move and respond to the forces acting on them. Antarctica contains active volcanoes beneath its ice sheet, creating hidden lakes of meltwater. These subglacial volcanoes could be melting the ice from below, creating environments where life might exist in complete darkness and warmth. It's a strange inversion of what we expect: heat rising from below, melting ice in pockets and chambers, creating liquid water in the heart of the frozen continent. Mount Erebus, which we've talked about, is Antarctica's most visible volcano. Its lava lake exposed to the surface, but there are others, hidden beneath ice, known only through seismic monitoring and ice-penetrating radar. Some are active, releasing heat that melts the ice directly above them. Others are dormant but still warm, their residual heat creating temperature anomalies in the ice sheet. The exact number is uncertain. It's hard to count volcanoes when they're buried under kilometers of ice, but estimates suggest dozens, possibly over 100 volcanic features beneath the Antarctic ice. The subglacial lakes created by volcanic heat are fascinating environments. They're dark, no light penetrates through kilometers of ice. They're warm, relatively speaking, with temperatures around or slightly above freezing, rather than the sub-zero temperatures of the ice above. They're isolated, potentially sealed off from the surface for thousands or millions of years. And they might contain life, extremophile microbes adapted to heat, darkness, and isolation, living off volcanic chemicals rather than sunlight. We haven't sampled most of these volcanic lakes yet. The technical challenges are immense. Drilling through kilometers of ice without contaminating the lake below, extracting samples without killing the organisms you're trying to find. Doing all of this in one of the most remote environments on Earth. But if we do find life in these volcanic lakes, it would expand our understanding of life's possibilities enormously. Life sustained by volcanic heat rather than the sun, thriving in darkness beneath ice, completely independent of the surface biosphere. It would be an Antarctic extremophile ecosystem, a hidden world of warmth in the coldest place on Earth, proof that life finds ways to exist in the most unlikely circumstances. The Antarctic Peninsula is one of the fastest warming regions on Earth, with temperatures rising by about 3 degree Celsius over the past 50 years. Ice shelves that were stable for thousands of years have collapsed in just weeks, changing the coastline dramatically. This narrow finger of land reaching towards South America is the part of Antarctica most immediately affected by climate change. A preview of what might happen to the rest of the continent if warming continues. The peninsula is warmer than the continental interior because it extends north into slightly less frigid latitudes and is influenced by ocean currents. But even here, temperatures historically stayed below freezing most of the year, and ice shelves, floating platforms of ice attached to the land, persisted for millennia. Ice shelves act as buttresses, holding back the glaciers on land, slowing their flow toward the ocean. They're important for stability, keeping the system in balance. Then the Larsen B ice shelf collapsed in 2002, an event we'll talk about more later. Other ice shelves have thinned, cracked, broken apart. The glaciers they were restraining have accelerated, flowing faster toward the ocean, contributing more to sea level rise. The peninsula is transforming, its geography changing in ways visible from satellites, measurable in years rather than centuries. Species are responding too. Adelie penguins, which prefer colder conditions and more sea ice, are declining in the peninsula while increasing farther south. Gentoo and chinstrap penguins, which tolerate warmer conditions, are expanding their range. Vegetation is appearing in areas previously too cold and dry. Moss banks are growing thicker, and in some areas, grass is sprouting where it hasn't grown for thousands of years. The Antarctic Peninsula is greening slightly at the edges as warmth creeps south. It's a transformation happening in real time, fast enough that scientists can watch it unfold, fast enough that researchers returning to the same sites years apart see obvious changes. For a place defined by stability and slow change, it's unsettling. Antarctica is supposed to be permanent, unchanging, the one place on Earth where human timescales don't matter. But the peninsula proves that even Antarctica responds to warming, that ice this ancient can still melt, that landscapes this stable can still transform when pushed hard enough. Antarctica is rising by about 5 millimeters per year as the bedrock rebounds from ice loss. The land is slowly recovering from the ice's weight, like a mattress expanding after you get up, a process that will continue for millennia. This rebound is evidence of ice loss happening now. The weight is decreasing, and the continent is responding, pushing upward as the pressure releases. Isostatic rebound operates on geological timescales usually. After the last ice age ended about 11,000 years ago, regions like Scandinavia and Canada that had been covered by massive ice sheets began rising as the ice melted. They're still rising today, thousands of years later, the process continuing long after the ice disappeared. Land rises slowly, adjusting to new equilibrium, taking centuries or millennia to fully rebound. But in Antarctica, we can measure it happening now, during our lifetimes, because ice loss is happening now. Satellites equipped with GPS receivers can measure land elevation changes with millimeter precision. The data shows uplift in areas where ice is thinning, West Antarctica particularly, where ice loss has been most dramatic. The uplift is small, just a few millimeters per year, but it's measurable, consistent, and accelerating in some areas as ice loss accelerates. There's something both fascinating and sobering about this. Fascinating because we're watching a geological process in action, seeing the planet respond to changing conditions in measurable ways. Sobering because the rebound is evidence of ice loss, proof that Antarctica's ice sheet is shrinking, that the weight pressing down on the continent is decreasing. The land rises because the ice is disappearing. It's a beautiful piece of science, measuring uplift to quantify ice loss. But it's also a warning sign, a signal that changes we thought would take centuries are happening in decades. The Gamburtsev Mountains, discovered in 2008, are buried under 4 kilometers of ice in East Antarctica. These ghost mountains are the size of the Alps, completely invisible at the surface, revealed only by radar and seismic surveys. Standing on the ice sheet above them, you'd see nothing but flat white expanse stretching to the horizon. No hint of the massive mountain range beneath your feet. The mountains were discovered by Soviet scientists in 1958 during the International Geophysical Year, using seismic measurements that detected rock buried deep beneath the ice. But their true scale and character weren't understood until recent surveys using ice-penetrating radar and gravity measurements. The data revealed peaks rising over 3,000 meters from base to summit, valleys carved between them, a complete alpine landscape preserved beneath ice, like a photograph sealed in amber. What makes the Gamburtsevs particularly mysterious is their age and condition. Mountain ranges erode over time, weather and water wear them down, smoothing peaks, filling valleys, gradually reducing elevation. The Gamburtsevs should have eroded flat long ago. They're ancient, probably over 1 billion years old in origin. Yet the peaks remain sharp, the valleys deep, the topography dramatic. How have they survived when they should have worn away? The answer seems to be the ice. The Gamburtsevs became ice-covered very early, perhaps 34 million years ago when Antarctica first froze. The ice protected them from erosion, preserving their topography while mountains elsewhere wore down. They've been frozen in time, literally, their shape maintained by the ice sheet that buried them. In a sense, Antarctica is preserving an ancient mountain range that would have disappeared anywhere else on Earth, keeping it intact beneath kilometers of ice, a geological treasure that we can map but never see. There's something haunting about ghost mountains. They exist, they're real, they're massive, but they're invisible, known only through instruments and data. Peaks that will never see sunlight again unless the ice melts. They're Antarctica's secret, a hidden landscape that predates the ice, that predates Antarctica's position at the pole, that has existed in darkness for millions of years, waiting. Antarctica has active underground rivers flowing beneath its ice sheet, carving channels in bedrock. These hidden waterways connect subglacial lakes, creating a dark, high-pressure plumbing system that we're only beginning to understand. Water flows beneath the ice despite the tremendous weight above it, finding pathways through rock and ice, moving from high elevations to low, seeking the ocean just as rivers do on the surface. The water comes from several sources. Some is meltwater, created by geothermal heat, warmth from Earth's interior, melting the base of the ice sheet. Some comes from pressure melting, the sheer weight of ice lowering water's melting point, so that ice at the bottom of the sheet, under immense pressure, melts even though temperatures are well below zero at atmospheric pressure. Some comes from friction. Moving ice grinding against bedrock generates heat, melting ice at the boundary. This subglacial water doesn't stay put. It flows, seeking lower elevations, carving channels in the bedrock, pooling in basins to create subglacial lakes, then overflowing and continuing toward the coast. Scientists have detected floods in these subglacial rivers, sudden movements of water from one lake to another, measurable from the surface as the ice sheet rises or falls slightly in response to water accumulation or drainage below. The system is dynamic, constantly changing, responding to ice sheet dynamics and geothermal variations. Some subglacial rivers flow continuously. Others are episodic, building up pressure until they burst through blockages and flood downstream. The water is dark, never seeing sunlight, carrying dissolved minerals from the bedrock, potentially hosting microbial life adapted to high pressure and complete darkness. It's a hydrological system operating entirely beneath ice, invisible except through instruments. A reminder that Antarctica has layers upon layers of hidden processes, systems operating in darkness that we're only beginning to map and understand. Blood falls in the McMurdo Dry Valleys flows with rusty red saltwater from beneath Taylor Glacier. The water has been trapped beneath the ice for over 1 million years, emerging iron-rich and creating a crimson stain on white ice. When it flows, which happens irregularly, depending on temperature and pressure conditions beneath the glacier, it looks like the ice is bleeding, a vivid red cascade against pristine white, startling and almost disturbing in its appearance. The red color comes from iron. The subglacial water is extremely salty, several times saltier than seawater, which keeps it liquid at temperatures around 5 degrees. This brine is in contact with bedrock, and over millennia it's dissolved iron from the rock. When the water emerges at blood falls and contacts oxygen in the air, the iron oxidizes, rusts, turning the water red-orange, the color of old blood or corroded metal. But blood falls is more than a curiosity. It's a scientific treasure. The water contains microbes, bacteria that have been isolated beneath the glacier for over 1 million years, living without sunlight, without oxygen, in conditions that would kill most life on Earth. These microbes survive through chemosynthesis, using iron and sulfur compounds for energy rather than photosynthesis. They represent an ecosystem completely independent of the sun, powered by chemistry rather than light, thriving in one of Earth's most extreme environments. The discovery has profound implications for astrobiology. If life can exist in blood falls, in salty, iron-rich water beneath a glacier, in complete darkness, at sub-zero temperatures, then similar life might exist elsewhere in the solar system. Europa's subsurface ocean, Enceladus's ice shell, perhaps even buried liquid water on Mars, if it exists. Blood Falls is a terrestrial analog for alien environments, a place where we can study how life might survive on worlds that seem utterly hostile. Standing at Blood Falls must be surreal. The dry valleys are already alien, bare rock, no vegetation, no visible life. And then this red water flowing from the glacier, staining ice and rock, looking like something from another planet. Which, in a sense, it is. It's water from a buried ocean, from a hidden world sealed beneath ice, emerging briefly into the dry Antarctic air before freezing again. A message from below, telling us that even here, even in these extreme conditions, life persists, patient and strange and utterly resilient. Antarctica's ice cores contain air bubbles that preserve the atmosphere from 800,000 years ago. Scientists can literally breathe ancient air, measuring exactly what Earth's atmosphere was like before modern humans existed. The ice acts as a time machine, each layer recording the year it fell as snow, trapping tiny samples of the atmosphere in bubbles as the snow compresses into ice. Drilling an ice core is a monumental undertaking. Teams set up drilling operations at remote sites, often on the high Antarctic plateau where ice is thickest and oldest. They drill down, extracting cylinders of ice, carefully preserving them, cataloging them, eventually transporting them to laboratories for analysis. The deepest cores penetrate over 3 kilometers, reaching ice that fell as snow hundreds of thousands of years ago. The bubbles in ice cores contain atmospheric samples frozen in time. Scientists can measure carbon dioxide concentrations, methane levels, oxygen isotope ratios, even trace gases present in tiny quantities. They can determine temperature by analyzing the isotopic composition of the water molecules that make up the ice. They can detect volcanic eruptions from ash layers and chemical signatures. They can see forest fires from distant continents through charcoal particles and chemical compounds deposited in Antarctic snow. What the ice cores reveal is sobering. Carbon dioxide levels varied naturally over the past 800,000 years, cycling between about 180 parts per million during ice ages and 280 ppm during warmer interglacial periods. But current CO2 levels, over 420 ppm as of recent measurements, are higher than anything in the ice core record. We've pushed atmospheric composition beyond the natural range that existed for hundreds of thousands of years, and we've done it in just a few centuries. The ice cores also show how tightly temperature and CO2 are linked. When CO2 rises, temperature rises. When CO2 falls, temperature falls. The correlation isn't perfect, other factors matter too, but it's strong, consistent, and visible across multiple glacial cycles. The ice provides evidence, preserved and irrefutable, of how Earth's climate system operates, how sensitive it is to greenhouse gas concentrations, how much change relatively small atmospheric shifts can produce. The ice in some parts of Antarctica is over 4 million years old at the very bottom of the sheet. This ice fell as snow when our earliest human ancestors were still millions of years from evolving. It accumulated during an era when Earth's climate was different, when the continents were positioned slightly differently, when the species alive on the planet were almost entirely different from those living today. And it's still there, compressed under the weight of younger ice, slowly flowing toward the ocean, holding memories of an Earth we can barely imagine. 4 million years is difficult to conceptualize. It's before the genus Homo evolved. It's before the last major glacial cycles began. It's a time when megalodon sharks still swam the oceans, when saber-toothed cats hunted in grasslands, when the world was fundamentally different from today. And through all that time, through the evolution of humans, through ice ages and warm periods, through the rise and fall of countless species, this ice has persisted, flowing slowly, melting at the edges, but surviving in the deep interior of Antarctica. Finding ice this old requires drilling in exactly the right places. Ice flows, deforms, mixes over time. Older ice gets compressed, thinned, sometimes folded or disturbed. Scientists use ice-penetrating radar and climate models to predict where the oldest ice might exist. Usually in areas where snowfall is low, ice movement is minimal, and the bedrock beneath creates stable conditions. They found 800,000-year-old ice in several locations. The search continues for even older ice, for the magical 1.5 million year mark that would span multiple glacial cycles and reveal new insights into Earth's climate history. When scientists extract ancient ice, they handle it with extraordinary care. It's irreplaceable. Once melted or contaminated, that atmospheric sample is lost forever. Each piece of ancient ice is a window into the past, a sample of an atmosphere that will never exist again, preserved by cold and pressure, and the patient accumulation of snow falling year after year for millions of years. Antarctica is an archive, the deepest and most complete record of Earth's recent climate history, written in ice and waiting for us to read it carefully, to learn from it, to understand what it's telling us about how our planet changes and why. Lake Vostok, buried under 4 kilometers of ice, is one of the largest subglacial lakes on Earth, about the size of Lake Ontario. It's been sealed from the surface for at least 15 million years, possibly harboring unique life. Forms evolved in complete isolation. The lake is a stable body of liquid water maintained by pressure, geothermal heat, and insulation from the ice above. A hidden ocean in the heart of Antarctica, dark and cold, and utterly separate from the surface world. The lake was discovered through seismic surveys and ice-penetrating radar. Scientists noticed that seismic waves behave strangely in a particular region. Instead of reflecting off bedrock, they indicated a layer of water beneath the ice. Further investigation revealed the lake's extent, roughly 250 kilometers long and 50 kilometers wide, with depths reaching over 500 meters. It's enormous, comparable to the Great Lakes, but completely hidden, known only through instruments and inference. Lake Vostok sits at the base of the ice sheet, sealed by the tremendous weight of ice above. The pressure at that depth is immense, over 350 atmospheres, enough to keep water liquid even at temperatures around 3 degrees C. The lake is thought to be fresh water, or at least fresher than seawater, created by melting ice over millions of years. It's oligotrophic, nutrient-poor, with very little organic matter to support life. Yet if life exists there, it would have to survive on whatever chemistry is available, possibly chemosynthesis using minerals dissolved from bedrock. Russian scientists reached Lake Vostok in 2012 after decades of drilling, but contamination concerns meant they couldn't sample the pristine lake water directly. They extracted ice from the very bottom of the ice sheet, ice that had been lake water, frozen onto the underside of the ice sheet as it flowed over the lake. Analysis of this accretion ice suggested the presence of bacteria, though whether they came from the lake or from contamination during drilling remains uncertain. The possibility of life in Lake Vostok is tantalizing. If organisms have been isolated for 15 million years, they might have evolved in unique directions, developing adaptations found nowhere else on Earth. They might represent a separate branch of the tree of life, cut off from surface ecosystems long enough to diverge significantly. Or the lake might be sterile, too cold and nutrient poor to support life even in isolation. We don't know yet. Lake Vostok remains largely unexplored, a hidden world that might contain revelations about life's possibilities, or might be empty, a sterile reservoir sealed beneath ice, waiting. Over 400 subglacial lakes exist beneath Antarctica's ice sheet, connected by a network of rivers and channels. Water flows between them, creating a hidden aquatic realm where pressure, darkness, and isolation might support ecosystems unlike anything on the surface. These lakes range from small ponds just a few kilometers across to massive bodies like Lake Vostok. Some are stable, sitting in bedrock depressions for millennia. Others fill and drain episodically, flooding downstream in pulses that can be detected from space. As the ice surface rises and falls, the network creates opportunities for life to spread. If microbes exist in one subglacial lake, they could potentially travel through connecting rivers to other lakes, colonizing new environments, creating a distributed ecosystem beneath the ice. This would be fundamentally different from surface ecosystems, where life is connected by atmosphere and ocean and land. The subglacial biosphere, if it exists, would be connected only by dark water flowing through rock and ice, carrying whatever life can survive the journey. Scientists have studied some lakes by drilling through the ice, extracting samples of the water and sediments below. Lake Whillans, drilled in 2013, revealed a thriving microbial ecosystem, thousands of cells per milliliter of water, diverse bacterial communities metabolizing various chemicals, evidence of an active, functioning ecosystem in complete darkness. The microbes were chemosynthetic, using chemical energy from minerals rather than sunlight. They represent an entirely different mode of life, independent of photosynthesis, operating on chemistry alone. If Lake Whillans hosts life, probably many other subglacial lakes do too. The connected network means that isolated pockets of life can interact, that biodiversity might be higher than we'd expect, that evolution is operating in this hidden realm just as it does on the surface. It's an Antarctic underworld, literally beneath the ice, dark and cold, and flowing with water that hasn't seen sunlight for millennia, possibly hosting ecosystems we're only beginning to discover. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of ice as a detector for ghostly particles from space. The pristine ice is so clear and dark that it can catch the faint flash when a neutrino, which normally passes through Earth unnoticed, actually collides with a water molecule. Neutrinos are subatomic particles produced by nuclear reactions in stars, supernovae, and other cosmic events. They barely interact with matter, passing through planets and stars as if nothing is there. Trillions pass through your body every second, and you never notice. But very rarely, a neutrino collides with an atomic nucleus. When it does, It produces a cascade of particles that emit Cherenkov radiation, a blue flash of light. IceCube detects these flashes using thousands of optical sensors embedded in the ice at depth between 1.5 and 2.5 kilometers. The sensors are connected by cables to computers at the surface, which record the timing and intensity of light flashes, reconstructing the neutrino's direction and energy. Why Antarctica? Because the ice is perfect for this. It's incredibly clear, less contamination than any ocean water, fewer impurities than ice anywhere else. It's dark, buried under enough ice that no sunlight penetrates. It's stable. The ice doesn't move much at these depths, keeping the sensors in fixed positions. And it's cold, which reduces noise from radioactive decay. In the ice itself, Antarctica provides a natural neutrino detector, a cubic kilometer of frozen water that humans have instrumented to watch for signals from distant cosmic events. IceCube has detected neutrinos from distant galaxies, from active galactic nuclei, from processes occurring billions of light years away. It's opened a new window on the universe, complementing telescopes that observe light and gravitational wave detectors that observe space-time ripples. Neutrinos carry information about processes invisible to other instruments, the cores of supernovae, the jets of black holes, the nuclear reactions in stellar interiors. And Antarctica's ice makes it possible, turning the frozen continent into an astronomical observatory, a detector for particles so elusive they're called ghost particles, captured in ice at the bottom of the world. Antarctica is the best place on Earth to find meteorites because dark rocks stand out on white ice and are preserved perfectly in the cold. The ice sheet acts like a conveyor belt, collecting meteorites over millennia and concentrating them in certain areas. Meteorites fall everywhere on Earth, more or less uniformly. A few thousand per year make it to the surface. But most fall in oceans or densely vegetated areas where they're difficult to find. Antarctica is different. When a meteorite falls on Antarctica, it lands on ice and stays there, preserved by the cold. The ice sheet flows, carrying the meteorite with it, sometimes for thousands of years and hundreds of kilometers. When the ice encounters mountain ranges or bedrock obstructions, the flow patterns concentrate meteorites in specific zones. The ice can also ablate, evaporate directly into water vapor, in areas with strong winds and low snowfall, leaving meteorites on the surface, accumulated from centuries of falls. The result is extraordinary. Antarctica has yielded over 40,000 meteorite specimens, more than all other continents combined. They're relatively easy to find. Walk across blue ice fields in areas where meteorites concentrate, and you'll likely see dark rocks sitting on the surface, obviously not belonging there. Scientists organize annual meteorite hunting expeditions, teams spending weeks traversing ice fields on snowmobiles, stopping to collect every dark rock they encounter. The meteorites are scientifically invaluable. They represent samples from asteroids, from Mars, from the Moon, pieces of other worlds delivered to Earth for free, requiring only the effort to find and collect them. Antarctic meteorites have taught us about the composition of the asteroid belt, the geology of Mars, the early solar system's chemistry. Some are incredibly rare, for instance, Martian meteorites, which represent pieces of Mars blasted into space by asteroid impacts and eventually falling to Earth. Most Martian meteorites have been found in Antarctica. There's something poetic about Antarctica as a meteorite repository. The continent preserves Earth's climate history in ice cores, preserves ancient landscapes beneath its ice sheet, and also preserves pieces of other worlds that fall from space, concentrating them for us to find. It's a natural museum, a collection of wonders from Earth and beyond, maintained by cold and ice and isolation. Some Antarctic meteorites are actually pieces of Mars, blasted from the red planet by ancient impacts and fallen to Earth. These Martian rocks have taught us more about Mars than decades of telescope observations, bringing the planet's geology directly to our laboratories. They're incredibly rare. Of the tens of thousands of meteorites found in Antarctica, only about 200 are confirmed to be from Mars. But those 200 are treasures, fragments of another planet that we can hold, analyze, and learn from. How do we know they're from Mars? Through chemical analysis. Martian meteorites contain trapped gas bubbles, pockets of atmosphere from Mars sealed inside when the rocks crystallized. When scientists analyzed these gases, they found they matched the Martian atmospheric composition measured by Viking landers in the 1970s. Very different from Earth's atmosphere, distinctive in its isotope ratios and chemical makeup. It's unambiguous evidence. These rocks came from Mars. The meteorites tell us about Martian geology. What kinds of rocks form there? What minerals are present? What the planet's interior chemistry is like. Some are basalts, volcanic rocks similar to those on Earth, but with subtle chemical differences reflecting Mars's unique evolution. Others are breccias, rocks formed from impact debris, telling stories of violent collisions on the Martian surface. A few contain minerals that suggest water was present when they formed, evidence of ancient Martian environments very different from the cold, dry desert Mars is today. One Martian meteorite, ALH 84001, caused tremendous controversy in 1996 when scientists claimed it contained evidence of fossilized Martian bacteria. The evidence included microscopic structures that resembled bacterial fossils, chemical signatures associated with life, and mineral formations that on Earth are typically produced biologically. The claim remains disputed. Most scientists think the features can be explained through non-biological processes, but the possibility, however remote, that we might have found evidence of Martian life in an Antarctic meteorite captured public imagination and reinvigorated Mars exploration. These rocks traveled millions of kilometers from Mars to Earth, surviving ejection from Mars, years or millions of years drifting in space, fiery entry through Earth's atmosphere, and finally landing on Antarctic ice where they waited for us to find them. They're cosmic messengers, pieces of another world delivered to ours, preserved in ice until curious humans came looking. Antarctica gives us many gifts, but Martian meteorites might be among the strangest and most valuable. The South Pole Telescope studies the cosmic microwave background, the afterglow of the Big Bang. Antarctica's dry air and high altitude create some of the clearest views of the early universe available anywhere on Earth. The telescope sits at Amundsen Scott Station, operating in conditions that would disable most instruments. Temperatures around 60 degrees C in summer, dropping to 80 degrees C or colder in winter. Winds that can exceed 100 kilometers per hour, and months of darkness when the sun never rises. The cosmic microwave background is radiation left over from when the universe was only 380,000 years old, when it cooled enough for atoms to form and light to travel freely for the first time. This radiation has been traveling through space for 13.8 billion years, stretched and cooled by the universe's expansion until it's now a faint microwave signal at a temperature of about 2.7 Kelvin, just above absolute zero. It fills the entire sky uniformly, but tiny temperature variations, differences of millionths of a degree, encode information about the universe's structure, composition, and evolution. Observing the cosmic microwave background requires extremely dry air because water vapor absorbs microwave radiation. Antarctica's air is phenomenally dry. The South Pole has precipitable water vapor levels that can drop below 0.2 millimeters, drier than most desert locations, drier even than some high-altitude observatories. This dryness, combined with the altitude, the ice sheet elevates the South Pole to about 2,935 meters, creates conditions where the atmosphere interferes minimally with observations. The South Pole Telescope has made fundamental discoveries about dark energy, the mysterious force accelerating the universe's expansion. It's mapped large-scale structures in the distant universe, detected galaxy clusters billions of light-years away, and measured properties of the cosmic microwave background with exquisite precision. All of this happens at the South Pole, where the telescope operates robotically through winter, where humans can barely survive outside for more than a few minutes, where the nearest help is thousands of kilometers away. Antarctica becomes an astronomical observatory, a place where the extreme conditions that make it nearly uninhabitable for life also make it perfect for observing the cosmos. Microorganisms discovered in Antarctica's ice can survive extreme cold, radiation, and near-total nutrient deprivation. These extremophiles are models for how life might exist on Jupiter's moon Europa or Saturn's moon Enceladus, where similar conditions prevail. They challenge our assumptions about life's requirements, demonstrating that organisms can survive in environments we'd consider utterly sterile and hostile. Antarctic extremophiles have been found in ice cores, in subglacial lakes, in the dry valleys, in glacial ice, even in snow. They employ various survival strategies. Some produce antifreeze proteins that prevent ice crystals from forming inside cells. Others enter dormancy, shutting down all metabolic activity and waiting, sometimes for thousands of years, until conditions improve. Some can repair DNA damage from radiation and desiccation, fixing breaks and mutations that would kill most organisms. The psychrophiles, cold-loving microbes, are particularly fascinating. They've adapted to function at temperatures where most biochemistry stops working. Their enzymes operate efficiently near or below freezing. Their cell membranes remain fluid at temperatures that would freeze most organisms solid. They grow slowly, sometimes taking weeks to divide even once, but they grow, metabolizing, reproducing, carrying on the fundamental processes of life in conditions that seem impossible. These organisms aren't just curiosities, they're astrobiological test subjects. Europa has a subsurface ocean beneath an ice shell kilometers thick. The conditions there, cold, dark, isolated from the sun, possibly with hydrothermal vents providing chemical energy, might resemble Antarctic subglacial lakes. If life evolved in Europa's ocean, it might be similar to Antarctic extremophiles, using the same strategies to survive. Enceladus has geysers erupting from its south pole, spraying water from a subsurface ocean into space. The water is salty, contains organic molecules, and has evidence of hydrothermal activity. Again, conditions potentially similar to what we find beneath Antarctic ice. By studying Antarctic extremophiles, we learn what life needs at minimum, what conditions are survivable, what metabolisms can operate in extreme environments. Antarctica becomes a laboratory for astrobiology, a place where we study life at its limits to understand where else in the solar system or the universe life might exist. Scientists have drilled through over 3.5 kilometers of ice to reach subglacial lakes without contaminating them. The drilling technology uses hot water and sterile equipment, designed to protect alien-like ecosystems that might exist in the dark waters below. It's an extraordinary technical achievement, comparable in difficulty to deep ocean drilling, but with the added challenge of working in Antarctica's extreme cold. The process works like this. First, melt massive amounts of snow to create a water reservoir. Heat that water to near boiling. Pump it down a drill hole under high pressure, melting through the ice. Recirculate the water, filtering and reheating it, maintaining a continuous flow that melts downward at a rate of several meters per hour. The drill doesn't cut or grind, it melts, leaving a clean hole with smooth walls. Contamination prevention is crucial. The drill water is filtered and UV sterilized. The drill equipment is cleaned meticulously. The entire operation is designed to minimize introducing surface microbes into the pristine lake below. This matters both for science, contamination would ruin the samples, and for ethics. If unique ecosystems exist in subglacial lakes, we have a responsibility not to contaminate them with surface organisms that might outcompete or destroy the native life. When the drill reaches the lake, scientists have only hours to work before the hole begins to refreeze. They lower sampling instruments, extract water, retrieve sediment cores, measure temperature and chemistry, all under immense time pressure. The samples are immediately preserved, frozen or refrigerated, transported to laboratories for analysis. The hole refreezes within days, sealing the lake again, protecting it from further disturbance. The technology developed for Antarctic subglacial lake exploration has direct applications for planetary science. If we ever send a mission to Europa or Enceladus to drill through the ice and sample the oceans below, we'll use techniques refined in Antarctica. The continent becomes a testing ground, a place where we practice for missions to other worlds, where we learn how to explore ice-covered oceans without contaminating them, where we develop the tools and protocols needed to search for life in the most difficult environments imaginable. Aurora australis, the southern lights, are visible year-round from Antarctica, but best seen during the winter darkness. The lights dance directly overhead at the magnetic South Pole, creating shimmering curtains of green, red, and purple in the endless night. They're caused by solar wind, charged particles from the sun, interacting with Earth's magnetic field and atmosphere. The particles spiral along magnetic field lines toward the poles, where they collide with atmospheric gases, exciting atoms, and causing them to emit light. The colors depend on which gases are excited and at what altitude. Green, the most common color, comes from oxygen at lower altitudes, around 100 to 200 kilometers up. Red comes from oxygen at higher altitudes, where the atmosphere is thinner. Purple and blue come from nitrogen. The lights move and shimmer because the solar wind is turbulent, varying in intensity and direction, creating waves and pulses in Earth's magnetosphere that translate into visible motion in the aurora. Antarctic auroras are particularly spectacular because Antarctica sits beneath the auroral oval, the ring-shaped region where auroras most commonly occur. At the magnetic South Pole, the aurora is directly overhead rather than on the horizon, creating a dome of light that spans the entire sky. During strong solar storms, the aurora intensifies, brightening until you can read by its light, rippling and pulsing with such vigor that it seems alive. Researchers at Antarctic stations describe the aurora as one of the most mesmerizing experiences of winter over. In the months of darkness, the southern lights become a constant presence, a reminder that the sun still exists even though it's below the horizon, a connection to the cosmos playing out in the sky every night. Some nights are quiet, just a faint glow on the horizon. Other nights are spectacular, the sky filled with dancing light, colors shifting and flowing, curtains unfurling and folding, an atmospheric performance that continues for hours. The aurora is physics made visible: magnetism, solar radiation, atmospheric chemistry, all combining to create beauty. Antarctica, dark for months, becomes a theater where the universe performs, where the solar wind's invisible violence translates into silent light, shows watched by a handful of humans isolated at the bottom of the world. The ozone hole was first discovered over Antarctica in 1985, revealing humanity's impact on the atmosphere. Each spring, ozone levels drop by up to 70%, creating a gap in Earth's protective shield where ultraviolet radiation pours through. The discovery was shocking. Scientists expected some ozone depletion from industrial chemicals called chlorofluorocarbons, CFCs, but they didn't expect such dramatic loss concentrated over Antarctica. Why Antarctica? The answer involves chemistry and meteorology. During Antarctic winter, temperatures in the stratosphere drop low enough for polar stratospheric clouds to form, clouds made of ice crystals in the upper atmosphere. These clouds provide surfaces where chemical reactions occur, converting stable chlorine compounds from CFCs into reactive chlorine species. When spring arrives and sunlight returns, these reactive chlorine molecules destroy ozone through catalytic reactions. A single chlorine atom can destroy thousands of ozone molecules before it's removed from the stratosphere. The polar vortex, strong winds that circle Antarctica in winter, isolates the stratospheric air over the continent, preventing mixing with ozone-rich air from lower latitudes. This isolation allows ozone destruction to proceed unchecked, creating the hole. When spring progresses and the vortex breaks down, ozone-depleted air mixes with surrounding air, and the hole gradually heals, only to reform the following winter. The consequences of ozone depletion are serious. Ozone absorbs ultraviolet B radiation, which causes skin cancer, cataracts, and immune system suppression in humans, and damages phytoplankton and ecosystems. The ozone hole over Antarctica means that during spring, UV levels can be dangerously high, affecting Antarctic marine life, particularly phytoplankton at the base of the food web. But there's hope. The Montreal Protocol, signed in 1987, banned CFC production globally. Atmospheric CFC concentrations have been declining since the late 1990s. The ozone hole is healing, slowly but measurably. Observations show it's smaller than it was in the early 2000s, and models predict it will recover to pre-1980 levels by around 2070. Antarctica became the canary in the coal mine, the place where humanity's atmospheric impact became undeniable, and also the place where we can measure our success in addressing that impact. Research stations in Antarctica study everything from glaciology to astrophysics, with over 5,000 scientists working there in summer. The continent has become a natural laboratory where extreme conditions allow experiments impossible anywhere else. Stations range from small summer-only facilities with just a few researchers to large year-round bases like McMurdo, which operates more like a small town during peak season. The research is extraordinarily diverse. Glaciologists drill ice cores and study ice sheet dynamics. Biologists catalog marine life and study adaptations to cold. Atmospheric scientists launch weather balloons and measure ozone. Astronomers operate telescopes that observe everything from the cosmic microwave background to neutrinos. Geologists study rocks and search for meteorites. Oceanographers measure currents and study the Southern Ocean. The continent supports dozens of scientific disciplines, all taking advantage of Antarctica's unique conditions. Living at research stations requires adaptation. The isolation is profound. During winter, evacuation is impossible for months. Medical emergencies must be handled on site, and station crew includes doctors and dentists. Supplies arrive once or a few times per year, so everything must be planned carefully. Fresh food runs out within weeks of the last resupply, and winter-over crews subsist on frozen and shelf-stable supplies. Communication with the outside world is possible via satellite, but delays and limited bandwidth make real-time conversation difficult. Yet people choose this life, spending months or years in Antarctica because the science is that compelling, the experience that unique. They describe a sense of purpose and camaraderie that's rare in normal life. Everyone depends on everyone else. The work matters. The data collected in Antarctica contributes to our understanding of climate, biology, astronomy, geology, and the environment, despite its harshness, is extraordinarily beautiful. The ice, the sky, the silence, these become part of the experience, transforming what could be mere endurance into something approaching transcendence. Antarctica's silence is so profound that researchers can hear their heartbeat in outdoor quiet moments. With no trees, traffic, or insects, the absence of sound becomes its own presence, a rare experience in our noisy world. In most places on Earth, you never experience true silence. There's always something: wind rustling leaves, distant traffic, birds, insects, the hum of electrical equipment. But in Antarctica's interior, far from stations and machinery, you can find silence so complete it's almost disorienting. The ice absorbs sound rather than reflecting it. There's no vegetation to rustle, no animals calling, often not even wind. You can hear your own breathing, your heartbeat, the creak of snow under your boots. Some researchers describe it as oppressive at first, this total absence of ambient sound. We're so accustomed to background noise that its absence feels wrong, unnatural. But over time, many come to treasure the silence, finding in it a kind of peace impossible to achieve anywhere else. The silence isn't always total. Sometimes the ice speaks. Glaciers groan and crack, creating deep rumbling sounds that travel for kilometers. Ice shelves calving into the ocean produce thunderous roars. Katabatic winds can rise suddenly, transforming silence into howling chaos in minutes. But between these events, the silence returns, deep and patient and all-encompassing. There's a meditative quality to Antarctic silence. It strips away distraction, focusing attention inward or on the immediate environment. Researchers describe spending hours in this silence, working, thinking, simply existing without the constant sensory bombardment that characterizes modern life. It's a kind of reset, a reminder of what baseline quiet actually means. And when they return to civilization, the noise is shocking. Traffic sounds aggressive, crowds overwhelming. The constant background hum of modern life suddenly apparent in ways it never was before. Antarctica recalibrates perception, teaching appreciation for silence and awareness of sound. Climate scientists study ice cores to understand past climate changes and predict future ones with remarkable precision. Each layer of ice is like a page in Earth's diary, recording temperature, snowfall, volcanic eruptions, and even forest fires from thousands of miles away. The ice cores are archives, physical records of atmospheric conditions stretching back hundreds of thousands of years, readable through careful analysis. The process of reading ice cores is sophisticated. Scientists measure stable isotope ratios, deuterium and oxygen-18, which vary with temperature, allowing reconstruction of past temperatures. They analyze trapped air bubbles for greenhouse gas concentrations. They measure dust and aerosol particles to understand atmospheric circulation and continent conditions. They identify volcanic ash layers, which can be correlated with known eruptions to provide time markers. They even detect traces of human activity, lead from Roman silver smelting, radioactive isotopes from nuclear weapons testing, industrial pollutants from the modern era. The precision is astounding. In the most recent ice, from the past few centuries, layers can be distinguished year by year, sometimes season by season. Scientists can tell you what the temperature was in Antarctica in 1816, the year without a summer, following the massive Tambora eruption. They can measure how much volcanic sulfate fell in 1783 from the Laki eruption in Iceland. They can track the rise of atmospheric CO2 from the Industrial Revolution, watching it climb from 280 parts per million in 1800 to over 420 ppm today. What ice cores reveal is both reassuring and alarming. Reassuring because they show that climate models work. When scientists use past conditions as inputs, the models accurately predict past temperatures and atmospheric composition, validating our understanding of climate physics. Alarming because they show how unusual current conditions are. The rate of CO2 increase is faster than anything in the ice core record. Temperatures are rising faster than natural variations would predict. We're pushing Earth's climate system into territory it hasn't experienced for millions of years, and we're doing it in the span of a few human lifetimes. GPS measurements show that parts of the West Antarctic ice sheet are losing ice at accelerating rates. Some glaciers are thinning by several meters per year, a pace that could fundamentally reshape global coastlines within centuries. The measurements are precise. GPS receivers mounted on bedrock near glaciers record position, changes with millimeter accuracy, revealing how the ice is moving, how fast it's flowing, how much mass it's losing. The technique works by tracking ice velocity and thickness changes. As glaciers thin, they flow faster because there's less resistance. As they flow faster, they deliver more ice to the ocean. The process can become self-reinforcing. Faster flow leads to more thinning, which leads to even faster flow. Scientists call this marine ice sheet instability, and it's particularly concerning in West Antarctica, where much of the ice sheet rests on bedrock below sea level. The Thwaites Glacier, nicknamed the Doomsday Glacier, is one of the most concerning. It's losing around 50 billion tons of ice per year, and the rate is increasing. The glacier is grounded on bedrock that slopes downward inland, meaning that as the grounding line retreats, the boundary where ice lifts off bedrock and begins floating, it exposes deeper ice to ocean water, potentially triggering faster melting and retreat. If Thwaites collapsed completely, it could contribute over 0.5 meter to global sea level rise, and it might destabilize surrounding glaciers, potentially adding several meters more. The GPS data, combined with satellite observations and ice-penetrating radar, paints a clear picture. West Antarctic ice loss is accelerating. What was a trickle in the 1990s has become a flow in the 2020s. The ice sheet is responding to warming ocean water, melting it from below, thinning the floating ice shelves that buttress the grounded ice behind them. As shelves thin and collapse, the glaciers they restrained speed up, delivering more ice to the ocean. It's not unstoppable yet. There's still debate about how fast collapse might proceed, whether natural variations might slow it, whether feedback mechanisms might stabilize the ice. But the trend is clear and concerning. Antarctica, once thought to be stable on human timescales, is changing measurably within decades. The GPS receivers record this change precisely, millimeter by millimeter, building a data set that documents one of the most significant transformations happening on Earth right now. The Don Juan Pond in the McMurdo Dry Valleys is so salty it never freezes, even at temperatures below 50 degrees C. It's the saltiest body of water on Earth, more concentrated than the Dead Sea, creating a Martian analog environment for astrobiological research. The pond is small, only about 100 meters long and a few centimeters deep in most places, but chemically extraordinary. The salinity comes primarily from calcium chloride, the same compound used for de-icing roads. Don Juan Pond is about 40% salt by weight, compared to seawater's 3.5% and the Dead Sea's 34%. This extreme salinity lowers the freezing point dramatically. Pure water freezes at 0 degrees C. Seawater freezes around 2 degrees C. Don Juan Pond remains liquid to at least 50 degrees, possibly lower. It's essentially concentrated brine, so salty that almost nothing can live in it. The pond's water source is mysterious. The dry valleys receive almost no precipitation, yet the pond persists. Scientists think the water comes from the atmosphere. Incredibly, the air, even in the dry valleys, contains trace moisture, and the pond's calcium chloride is hygroscopic, absorbing water vapor from the air. The pond might be pulling moisture directly from the atmosphere, accumulating it over time, creating liquid water in one of the driest places on Earth through sheer chemical attraction. Don Juan Pond serves as an analog for potential brines on Mars. Orbital observations suggest that Mars has salty water near the surface in some regions, too salty to freeze at Martian temperatures. If life exists on Mars today, it might be in environments like Don Juan Pond, extremely salty, liquid at very cold temperatures, sustained by atmospheric moisture rather than rainfall. Studying the pond helps us understand what Martian brines might be like, what chemistry occurs in them, whether life could possibly adapt to such extreme conditions. It's a surreal place to visit, apparently. A shallow red-brown pool in a valley devoid of life, surrounded by bare rock and ice, never freezing despite temperatures that would turn normal water solid. It looks alien because, in a sense, it is. a chemical environment so extreme that it barely exists anywhere on Earth, but might be common on Mars. Antarctica offers this window, this terrestrial analog to another planet, a place where we can study alien conditions without leaving Earth. Antarctic sea ice behaves differently than Arctic ice. It expands and contracts seasonally, but doesn't have the same multi-year ice. Each year, most Antarctic sea ice melts and reforms, creating dramatic seasonal changes in the continent's effective size. In winter, sea ice can extend 1,000 kilometers or more from the Antarctic coastline, effectively doubling the continent's size. In summer, most of it melts, retreating to a narrow fringe around the coast or disappearing entirely in some regions. This seasonal cycle is extreme. Antarctica goes from around 3 million square kilometers of sea ice in February, the height of summer, to over 18 million square kilometers in September, at the peak of winter. That's an expansion of 15 million square kilometers, an area larger than Antarctica itself. The ice forms rapidly as temperatures drop, growing several centimeters per day during the coldest months, creating vast platforms of frozen ocean where emperor penguins breed and seals haul out. Arctic sea ice, by contrast, includes substantial multi-year ice that survives summer melting and persists year after year, growing thicker and more stable. Antarctic sea ice mostly lacks this. It forms in winter, melts in summer, and the cycle repeats. There are exceptions. Some sheltered bays and regions retain ice year-round. But in general, Antarctic sea ice is annual, seasonal, ephemeral. Why the difference? Geography and ocean circulation. The Arctic Ocean is largely enclosed by land, allowing ice to accumulate and persist. Antarctica is a continent surrounded by open ocean, with the Antarctic Circumpolar Current flowing around it. This current prevents ice from accumulating permanently. It gets carried away, broken up, melted by warmer waters from the north. The ice that forms each winter is largely new ice, growing from scratch as temperatures drop. This seasonal ice is crucial for Antarctic ecosystems. Krill depend on it for nursery habitat. Seals and penguins use it as platforms for resting and breeding. The algae that grow on its underside provide food for the entire Antarctic food web. When sea ice dynamics change, forming later, melting earlier, covering less area, the impacts ripple through the ecosystem. Antarctic sea ice is a temporary feature, present for only part of each year, yet ecosystems have adapted to depend on it, timing their life cycles to the ice's predictable rhythm. As climate changes and that rhythm becomes less predictable, species struggle to adapt. Scientists have discovered over 1,000 species of microbes in Antarctic ice that were previously unknown to science. These organisms challenge our understanding of life's limits, surviving in conditions that would kill most living things within minutes. They exist in tiny pockets of liquid water within the ice, in films of brine on ice crystal surfaces, in spaces between ice grains, microhabitats that remain liquid even in temperatures far below freezing because of salt concentrations or pressure or both. These microbes are astonishingly diverse. Bacteria, archaea, fungi, algae, entire ecosystems existing in what appears to be solid ice. They metabolize slowly, sometimes taking months or years to reproduce, living at a pace that makes geological processes seem rapid. Some are psychrophiles, adapted specifically to cold. Others are psychrotolerant, capable of surviving cold but preferring warmer temperatures. These might be dormant, waiting for conditions to improve, perhaps for thousands of years. The discovery of so many unknown species raises questions about biodiversity. If Antarctic ice, one of the most extreme environments on Earth, hosts over 1,000 unknown microbial species, how much biodiversity are we missing? Globally, how many microbes exist in extreme environments that we've barely explored? The estimates of total microbial diversity on Earth range from millions to possibly a billion species, and we've characterized only a tiny fraction. Antarctica hints at this vast unknown, revealing that even in places we assume are sterile, life persists in forms we never anticipated. These microbes also represent potential sources of novel biochemistry. Enzymes that function at extreme cold are valuable for industrial processes that require low temperatures. Antifreeze proteins might have medical applications. Metabolic pathways that operate under extreme stress might reveal new biochemical principles. Antarctica's hidden microbial diversity is both a scientific curiosity and a potential resource, a library of biological solutions to extreme conditions that might have applications we haven't imagined yet. The Antarctic Circumpolar Current is the world's largest ocean current, flowing continuously around the continent. It moves more water than all the world's rivers combined, isolating Antarctica climatically and oceanographically from the rest of Earth. The current flows from west to east, driven by powerful westerly winds that circle Antarctica in the roaring 40s and furious 50s latitudes. It's unobstructed by land, the only major ocean current that circles the globe continuously, and it's enormous, transporting around 134 million cubic meters of water per second. To put that in perspective, the Amazon River, Earth's largest river by discharge, carries about 209,000 cubic meters per second. The Antarctic Circumpolar Current moves more than 600 times that amount. It's not a single narrow stream, but a broad flow hundreds of kilometers wide, extending from the surface to depths of several kilometers. Within this flow, water masses of different temperatures and salinities mix and interact, creating complex oceanographic structures. The current acts as a barrier, isolating Antarctic waters from warmer waters to the north. This isolation helps maintain Antarctica's cold climate. Warm water can't easily flow south past the current, so the ocean around Antarctica stays cold year-round. The current also drives upwelling of deep ocean water, bringing nutrient-rich water to the surface and creating some of the most productive marine ecosystems on Earth. The nutrients support blooms of phytoplankton, which feed krill, which feed everything else in the Antarctic food web. But the current is changing. Warming climate is shifting the westerly winds that drive it, potentially altering the current's strength and position. Changes in the current affect Antarctic ice shelves. If warmer water penetrates farther south, it can melt ice from below more aggressively. Changes also affect global climate. The Antarctic Circumpolar Current connects the Atlantic, Pacific, and Indian Oceans, distributing heat and salt and carbon dioxide around the globe. What happens in the Southern Ocean doesn't stay in the Southern Ocean. It influences climate worldwide. The current is a planetary scale phenomenon, a conveyor belt connecting oceans, a barrier protecting Antarctica, a pump bringing nutrients to the surface. It's one of Earth's fundamental oceanographic features, and we're only beginning to understand how it might change and what those changes might mean for climate, ice, and ecosystems. Researchers in Antarctica can conduct experiments in whiteout conditions, where the ground and sky become indistinguishable. In these moments, depth perception vanishes completely, and people have walked into walls they couldn't see just meters away. Whiteouts occur when snow, fog, or cloud cover creates diffuse lighting with no shadows, no visual texture, nothing for the eye to focus on. Everything becomes uniform white in all directions. The disorientation is profound and immediate. Your brain relies on visual cues to establish up and down, near and far. Remove those cues, and balance becomes difficult. People describe feeling like they're floating, unable to tell if they're walking uphill or downhill, unable to judge distance to objects. A building 50 meters away might be invisible. A flag 10 meters away might seem impossibly far. Spatial sense fails completely. Whiteouts are dangerous for exactly this reason. Aircraft can't land. Pilots can't distinguish the horizon from the ground. People walking between buildings can become disoriented and lost within meters of safety. There are documented cases of researchers walking in circles just outside their stations, unable to find the entrance, despite being within sight distance under normal conditions. Some Antarctic stations string rope lines between buildings specifically for whiteout conditions, allowing people to navigate by touch when vision is useless. Yet whiteouts also offer an eerie kind of beauty. The world reduces to pure white, empty and featureless, almost meditative in its simplicity. Sound becomes the primary sense. You can hear but not see, creating a sensory inversion that's deeply strange. Some researchers describe whiteouts as peaceful. Once the initial disorientation passes, a kind of enforced stillness where nothing can be done except wait for conditions to improve. Antarctica strips away assumptions, revealing how much we depend on sensory information we take for granted. Vision seems so reliable until it isn't, until the world becomes uniform white and your eyes provide no useful information at all. It's humbling, this reminder that perception is fragile, that the solid world we think we see is actually a construction our brains build from sensory input, and remove that input, the construction collapses. Some Antarctic research stations maintain seed banks and data archives designed to survive global catastrophes. The ice makes Antarctica a natural deep freeze vault, preserving crucial information and biological samples for future generations. The logic is straightforward. Antarctica is isolated, stable, and cold. If catastrophe strikes elsewhere, war, pandemic, climate collapse, Antarctica's remoteness and extreme environment might protect whatever is stored there. The concept mirrors the Svalbard Global Seed Vault in the Arctic, which stores duplicate seeds from gene banks worldwide as a backup against disasters. Some Antarctic stations maintain similar collections, though smaller in scale. Seeds from important crops, genetic material from endangered species, microfilm archives of crucial documents, digital storage media kept frozen to extend their lifespan far beyond normal expectations. The ice itself acts as preservation. At Antarctic temperatures, biological materials remain viable far longer than they would anywhere else. Seeds that might last decades in normal storage can last centuries in Antarctic cold. DNA degrades slowly, proteins remain stable, chemical reactions essentially stop. It's passive preservation, requiring no energy input beyond maintaining the cold, which Antarctica does naturally. There's something simultaneously hopeful and melancholic about these archives. Hopeful because they represent planning for continuity, ensuring that if present civilization fails, future humans have seeds to plant and knowledge to rebuild. Melancholic because they acknowledge the possibility of catastrophic failure, the recognition that we might destroy what we've built and future generations might need these preserved remnants to start again. Antarctica becomes a vault, not just of ice and climate records, but of human knowledge and biological diversity, a backup drive for civilization stored in the most stable, remote location on Earth. It's a role the continent plays almost accidentally, its extreme conditions creating preservation capabilities we're only beginning to exploit intentionally. Ernest Shackleton's 1914 Endurance expedition became one of history's greatest survival stories when the ship was crushed by ice. All 28 crew members survived months on ice floes and a desperate 800-mile open boat journey, with Shackleton famously not losing a man. The expedition was attempting to cross Antarctica on foot, from the Weddell Sea to the Ross Sea, traversing the entire continent. They never even set foot on Antarctic land. The Endurance became trapped in sea ice in the Weddell Sea in January 1915. For months, the ship drifted with the ice, held fast, while the crew waited for the ice to release them. It didn't. The ice pressure grew stronger, crushing the ship's hull, forcing the crew to abandon her. They watched from the ice as the Endurance was slowly destroyed. Timbers cracking, hull collapsing, the ship that was their home, and their hope sinking beneath the ice in November 1915. What followed was survival against extraordinary odds. The crew camped on ice floes, drifting north as the ice carried them. When the floe they were on began breaking up, they launched 3 small boats and rowed to Elephant Island, a desolate rock at the edge of the Antarctic peninsula. From there, Shackleton and 5 others made a desperate 800-mile journey across the Southern Ocean in a 22-foot boat to reach South Georgia Island. They landed on the wrong side of the island and had to cross unmapped mountains to reach a whaling station. Shackleton then returned to Elephant Island and rescued the remaining crew members, over a year and a half after the Endurance was crushed. The story endures because of Shackleton's leadership. He kept morale up through impossible circumstances. He made decisions that prioritized crew welfare over the expedition's original goals. When things went catastrophically wrong, he adapted, focusing entirely on bringing everyone home alive. And he succeeded. Every single crew member survived, a testament to leadership, resilience, and luck in equal measure. The wreck of the Endurance was found in 2022, 107 years after it sank, lying on the seafloor at a depth of over 3,000 meters, remarkably well preserved in the cold Antarctic water. The discovery brought the story full circle, revealing that the ship that failed its mission but succeeded in bringing its crew home still exists, silent and dark beneath the ice, a monument to survival. Robert Scott's expedition reached the South Pole in 1912, only to discover Roald Amundsen had beaten them by 34 days. Scott and his 4 companions died on the return journey, just 11 miles from a supply depot that could have saved them. The story is one of the most famous tragedies in exploration history, a tale of courage, miscalculation, and terrible luck. Scott's team reached the South Pole on January 17, 1912, after months of grueling travel, hauling supplies on sleds, battling storms and cold, enduring temperatures that dropped below 40 degrees. They found Amundsen's tent already there, a Norwegian flag flying, a note left for Scott. The disappointment was crushing. All their effort, all their suffering, and someone else had arrived first. The pole itself offered nothing, just ice and cold, and the knowledge they'd come second. The return journey was doomed from the start. Temperatures were unseasonably cold, making travel more difficult. One team member, Edgar Evans, died from injuries and possibly hypothermia in February. Another, Lawrence Oates, deliberately walked out into a blizzard in March, knowing he was slowing the team down, saying, "I am just going outside and maybe some time." He never returned, sacrificing himself in an attempt to give the others a better chance. Scott and the two remaining companions, Edward Wilson and Henry Bowers, made it to within 11 miles of a supply depot called One Ton Depot, which contained food and fuel that could have saved them. But a blizzard pinned them down in their tent for days. Weakened by hunger, cold, and exhaustion, they couldn't continue. They died in their tent sometime in late March 1912. Their bodies and journals found by a search party 8 months later. Scott's final journal entries are heartbreaking. He wrote messages to the families of his companions, praising their courage. He wrote that they died honorably, having reached the pole even if they hadn't been first. His last entry reads, "For God's sake, look after our people." The search party buried them where they lay, collapsing the tent over them and building a cairn of snow on top. They're still there, somewhere beneath the ice sheet, slowly being carried toward the coast by the ice's flow, their story preserved in frozen silence. The Amundsen-Scott South Pole Station is built on stilts that can be raised as snow accumulates beneath it. The station literally rises higher each year as the ice sheet grows, a surreal sight in one of Earth's most extreme locations. The design is necessary because snow accumulation at the South Pole averages about 20 centimeters per year. Without accommodation for this accumulation, the station would be buried within decades. The station consists of a central elevated structure that houses living quarters, laboratories, and facilities for around 50 people in winter, and up to 150 in summer. The building sits on adjustable columns that can be hydraulically jacked upward as snow accumulates beneath. When the columns reach their extension limit, the building is jacked up further, and the columns are lengthened, allowing the station to continue rising indefinitely, staying above the growing ice surface. Living at the South Pole is extreme even by Antarctic standards. The altitude, effectively around 3,400 meters, due to the cold, dense air, causes altitude sickness for many arrivals. The winter darkness lasts 6 months. Temperatures regularly drop below 60 degrees, and the record low is 82.8 degrees. Evacuation is impossible during winter. No aircraft can land or take off in those temperatures and conditions. The winter over crew is completely isolated from March to October, roughly 230 days of total isolation. Yet people volunteer for this assignment. Scientists conduct research that can only be done at the South Pole. Neutrino detection, cosmic microwave background observations, atmospheric studies. The station operates the Ice Cube Observatory, the South Pole Telescope, and numerous other scientific instruments. Support staff keep the station running: power plant operators, mechanics, cooks, medical personnel, all of them choosing to spend a year at the most isolated research station on Earth. The station honors both Amundsen and Scott, the first two expeditions to reach the pole, one successful, one tragic. Inside the station, there's a library, a greenhouse where fresh vegetables grow under artificial light, a gym, communal spaces where the crew gathers. It's a remarkable outpost of human presence at the bottom of the world, a place where science and human endurance meet, where we've established continuous presence at one of the most hostile locations on the planet. Winter over crews in Antarctica are more isolated than astronauts on the International Space Station. During winter, evacuation is impossible for 9 months. Spacecraft can launch rescue missions faster than planes can reach polar bases. The isolation is total. No flights, no ships, no possibility of leaving or receiving visitors. The crew shrinks to a core group, maybe 15 to 50 people depending on the station, and they're on their own until spring. The isolation affects people differently. Some thrive, enjoying the quiet, the dark, the small community. Others struggle with cabin fever, social tensions, the psychological weight of being truly cut off. Stations screen carefully for winter over candidates, looking for psychological resilience, ability to work in close quarters, technical skills, and emotional stability. But you can't predict how someone will respond until they're actually there, weeks into darkness, with months still to go. Social dynamics become crucial. With no escape, conflicts must be resolved, or at least managed. People develop routines, traditions, rituals to mark time and maintain sanity. Many stations celebrate midwinter with a feast and celebration, marking the point where darkness begins to lessen, where spring, however distant, is at least approaching rather than receding. Some stations hold film festivals, themed parties, talent shows, anything to break the monotony and bring the crew together. The comparison to space is apt. Astronauts on the ISS can be evacuated within hours if necessary. A Soyuz capsule is always docked, ready for emergency return. Antarctic winter over crews have no such option. If medical emergency strikes, they deal with it themselves. Stations have doctors, but they're general practitioners with limited equipment, managing conditions that would require specialists and hospitals anywhere else. There are documented cases of doctors performing surgeries on themselves, treating their own conditions because there was literally no one else available. Yet the isolation also creates bonds. Winter over crews describe intense camaraderie, relationships forged in conditions that strip away pretense and superficiality. When your survival depends on the people around you, when you're all isolated together, experiencing the same darkness and cold and confinement, something shifts. The experience changes people. Almost everyone who winters over in Antarctica says they're different afterward, having endured something most humans never will. Antarctica has its own 300 Club, where people brave 100-degree temperatures by running naked from a 200-degree sauna to the South Pole marker. The 300-degree temperature swing creates an otherworldly experience, with breath freezing instantly and skin burning from the cold. It's a tradition at Amundsen Scott Station, a rite of passage for winter over crews, and it's exactly as crazy as it sounds. The procedure is simple. Heat the sauna to around 200 degrees, 93 degrees. Wait for outdoor temperatures to drop to 100 degrees, 73 degrees, or colder, which happens occasionally during winter. Stripped naked, or nearly so, most people wear boots to protect their feet from frostbite on the ice. Run from the sauna, across the snow, to the ceremonial South Pole marker, and back. The entire run takes maybe a minute, sometimes less. The experience is extreme. The moisture in your breath crystallizes instantly, falling as ice crystals, the whisper of stars Russians describe at Vostok. Your skin feels like it's burning. Cold feels identical to heat at these extremes, both triggering the same pain receptors. You can't breathe deeply because the air is so cold it hurts your lungs. Everything happens fast. Get to the pole, touch the marker, get back to the sauna before frostbite sets in. Why do people do this? Partly for bragging rights. It's a unique experience, possible only at the South Pole during the coldest winter nights. Partly for the story. Everyone who completes it has a tale no one else can claim. Partly because it represents mastery over Antarctica's extremes, a defiant assertion of human presence in conditions that should kill us. And partly just because it's there, a challenge presented by circumstance, something impossible anywhere else. The 300 Club is unofficial, unsanctioned, technically probably violates safety protocols, but it persists as a tradition, passed from one winter-over crew to the next, a ritual that marks membership in a very exclusive group, people who've experienced a 300-degree temperature swing in under a minute, naked at the South Pole, in the middle of Antarctic winter. It's absurd, dangerous, and somehow perfect for a place as extreme as Antarctica. Antarctica's ice reflects about 80% of the sun's radiation back into space, helping cool the entire planet. This albedo effect means ice loss doesn't just raise sea levels. It reduces Earth's natural air conditioning system. Fresh snow is among the most reflective natural surfaces on Earth, bouncing sunlight away before it can warm the surface. Dark surfaces, ocean water, rock, soil, absorb sunlight, converting it to heat. The difference is dramatic. Replace white ice with dark ocean, and you fundamentally change Earth's energy balance. The numbers matter. Antarctica reflects roughly 80% of incoming solar radiation. The ocean absorbs about 90%. So when ice melts and exposes ocean beneath, you go from reflecting most sunlight to absorbing most of it. This creates a feedback loop. Warming melts ice. Exposed dark surface absorbs more heat, which melts more ice, which exposes more dark surface. The process reinforces itself, accelerating once it begins. This feedback operates globally. Antarctic ice doesn't just affect Antarctic temperatures, it affects planetary climate. The massive white surface at the South Pole reflects sunlight that would otherwise warm Earth's surface, lose that reflective capacity, and global temperatures rise even beyond the direct warming from greenhouse gases. It's a second-order effect, a consequence of consequences, and it amplifies climate change in ways that aren't immediately obvious. The Arctic experiences this feedback more dramatically because Arctic sea ice is declining faster than Antarctic ice currently. But the principle applies everywhere ice exists. Glaciers, sea ice sheets, all of them contribute to planetary cooling through reflection. All of them, when melted, flip from cooling to warming, from light-colored surfaces that help stabilize climate to dark surfaces that destabilize it. Antarctica is Earth's refrigerator in multiple senses. It stores cold in the form of ice. It generates cold through radiative cooling, and it maintains cold globally by reflecting sunlight that would otherwise warm the planet. Damage any of these functions, and the effects ripple worldwide. The ice isn't just frozen water. It's a critical component of Earth's climate system, actively maintaining conditions that make the current climate possible. If the West Antarctic ice sheet collapsed completely, It would raise global sea levels by about 3.3 meters. This scenario would redraw coastlines worldwide, submerging cities like Miami, Bangkok, and Shanghai beneath the waves. It sounds catastrophic, and it would be, but it's worth understanding that collapse doesn't mean sudden or immediate. We're talking about processes that unfold over decades or centuries, not weeks or months. The West Antarctic ice sheet is particularly vulnerable because much of it rests on bedrock below sea level, in what's called a marine ice sheet configuration. The ice is grounded on bedrock, but the bedrock slopes downward, inland rather than upward. This matters because of how ice retreats. When the grounding line, where ice lifts off bedrock and begins floating, retreats into deeper water, more ice is exposed to ocean melting. The process can become self-reinforcing, with retreat leading to more retreat, potentially unstoppable once triggered. Scientists debate whether we've already passed the threshold for West Antarctic ice sheet instability. Some studies suggest that glaciers like Thwaites and Pine Island have entered irreversible retreat, that the process is now ongoing regardless of what we do with emissions. Other studies are more cautious, suggesting that reducing ocean warming could still slow or stabilize retreat. The uncertainty is genuinely uncertain. We don't know enough about the ice sheet's internal structure, about bedrock topography beneath it, about ocean circulation that brings warm water to the ice. What we do know is that 3.3 meters of sea level rise would be transformative. It wouldn't happen overnight. Even in pessimistic scenarios, collapse might take several centuries, but eventual inundation of low-lying areas would displace hundreds of millions of people. The Mekong Delta, the Nile Delta, Bangladesh, the Netherlands, Florida, all dramatically affected. Island nations would simply vanish. Trillions of dollars of infrastructure would be lost. The West Antarctic ice sheet represents one of Earth's major tipping points, a threshold we might cross that fundamentally changes the planet for thousands of years. The ice accumulated over millions of years. We might destabilize it in a few centuries, and once gone, it won't return. Earth would need another ice age to rebuild an ice sheet that size, a transition that takes tens of thousands of years. We're potentially making a decision, through action or inaction, that affects planetary geography for millennia. Ocean currents that begin in Antarctica help drive the global oceanic circulation that regulates climate worldwide. Cold, dense water sinking around Antarctica flows along ocean floors toward the equator, creating a planetary-scale conveyor belt. This circulation, called the thermohaline circulation, or sometimes the global conveyor belt, distributes heat and nutrients around the world's oceans, influencing weather patterns, marine ecosystems, and climate stability. The process starts when Antarctic sea ice forms. As seawater freezes, it excludes salt, creating extremely salty cold water that's denser than the surrounding ocean. This dense water sinks, forming Antarctic bottom water, which flows north along the ocean floor into the Atlantic, Pacific, and Indian Oceans. The flow is massive, around 10-20 million cubic meters per second, carrying cold water into the deep ocean, where it circulates slowly, taking centuries or even a millennium to complete a full cycle. This deep water circulation matters for climate regulation. It transports heat from tropical regions toward the poles and brings nutrient-rich deep water to surface regions where upwelling occurs. Changes in Antarctic circulation affect the entire system. If fresh water from melting ice dilutes the surface water around Antarctica, it reduces density differences that drive sinking. Weaken the sinking, and you weaken the entire circulation, potentially altering global climate patterns in ways we're only beginning to understand. Evidence suggests the circulation is already changing. Observations show that Antarctic bottom water formation has declined in recent decades, and the water is becoming warmer and fresher, less dense, less effective at driving deep circulation. The changes are subtle so far, but they're measurable and consistent with warming climate predictions. If circulation weakens substantially, it could affect everything from European climate to tropical monsoons to marine ecosystem productivity. Antarctica sits at the origin point of this planetary circulation system, the engine that drives deep ocean flow. What happens there doesn't stay there. It propagates through ocean basins, affecting climate zones thousands of kilometers away. The continent's role in Earth's climate extends far beyond reflecting sunlight or storing ice. It actively drives circulation that regulates heat distribution across the planet. Antarctica's ice sheet gains snow on top while losing ice to the ocean below, in a delicate balance that's now tipping. Recent measurements show losses exceeding gains, with the continent contributing more to sea level rise each year. Understanding this balance requires accounting for all inputs and outputs: snow accumulation, surface melting, ice discharge into the ocean, basal melting beneath ice shelves. Traditionally, Antarctica was thought to be relatively stable. Snow accumulation roughly balanced ice loss, with the ice sheet maintaining approximately constant mass. But satellite measurements beginning in the early 2000s revealed this wasn't true. Antarctica is losing mass, and the rate is accelerating. The ice sheet lost around 40 billion tons per year in the 1980s, 50 billion tons per year in the 1990s, 147 billion tons per year in the 2010s. The trend is clear and concerning. The losses come primarily from West Antarctica and the Antarctic Peninsula, where warm ocean water is melting ice from below. East Antarctica, the larger portion of the ice sheet, is close to balanced, or possibly gaining slightly, due to increased snowfall from warmer, moister air. But the West Antarctic losses overwhelm East Antarctic gains, resulting in net mass loss for the continent as a whole. Measuring ice sheet mass balance requires sophisticated instruments. Satellite gravimetry, measuring Earth's gravitational field from orbit, detects mass changes as ice accumulates or disappears. Satellite altimetry measures ice surface elevation changes over time. GPS stations on bedrock measure uplift as ice load decreases. Climate models estimate snowfall and surface processes. Combining all these measurements gives a comprehensive picture of ice sheet health. The picture isn't reassuring. Antarctica is losing ice, the rate is accelerating, and the losses are concentrated in regions most vulnerable to marine ice sheet instability. We're not yet seeing catastrophic collapse. These are incremental changes, measurable in gigatons but spread over a massive ice sheet. But the trajectory is toward greater loss, faster contribution to sea level rise, and potentially crossing thresholds that trigger irreversible retreat. The balance that maintained Antarctica's ice for thousands of years is tipping, and we're watching it happen in real time. Katabatic winds in Antarctica can accelerate from calm to over 300 km/h in minutes as cold air rushes down from the polar plateau. These winds are among Earth's most powerful surface-level phenomena, capable of scouring ice and rock with relentless force. They form through a simple mechanism made extreme by Antarctica's conditions. Air over the high interior plateau cools through radiative loss, becoming denser than the air around it. Gravity pulls this dense air downslope toward the coast, and as it descends, it accelerates. The descent from Antarctica's interior to the coast can cover vertical distances of 2,000 to 3,000 meters, and the air accelerates all the way down, funneled through valleys and compressed by topography. By the time katabatic winds reach the coast, they're often hurricane force or stronger, blowing with sustained speeds that would classify as Category 3 or 4 hurricanes if they occurred over water. The world record for fastest wind gust ever recorded was 408 km/h at Barrow Island, Australia. But Antarctica regularly experiences winds over 300 km/h in certain locations. Commonwealth Bay in East Antarctica is one of the windiest places on Earth, with average annual wind speeds around 80 km/h, not gusts, average speeds, and gusts regularly exceeding 240 km/h. Douglas Mawson's 1911-1914 expedition established a base there and endured winds so constant and powerful that routine outdoor work became nearly impossible. They called it the home of the blizzard, and Mawson's writings describe winds strong enough to knock people over, to tear apart equipment, to make the simple act of walking outside an exhausting struggle. Katabatic winds create unique hazards. They can arise quickly with little warning. They carry ice particles that scour exposed surfaces and create zero visibility. They can cool temperatures further through wind chill, turning 20 degrees C into effective temperatures below 60 degrees. And they're persistent. Unlike normal storms that pass through, katabatic winds can blow for days or weeks, driven by the constant process of cold air draining from the plateau. Yet they're also a natural phenomenon, part of Antarctica's climate system, driven entirely by the continent's topography and cold. They represent Antarctica's tendency toward extremes, not just cold, but also the winds that cold creates, making an already harsh environment even more hostile, reminding anyone who ventures there that this continent doesn't tolerate human presence easily. The collapse of the Larsen B ice shelf in 2002 happened in just 6 weeks, shocking scientists who expected stability for decades. An ice shelf the size of Rhode Island disintegrated in weeks, revealing how quickly Antarctic systems can change. Ice shelves are floating platforms of ice attached to the coast, fed by glaciers flowing from the interior. They don't contribute directly to sea level rise when they melt because they're already floating, but they matter because they buttress the glaciers behind them, slowing ice flow into the ocean. Larsen B had been stable for at least 12,000 years, probably much longer. Through the entire Holocene, the current geological epoch spanning all of recorded human history, this ice shelf persisted, surviving natural climate variations, holding back glaciers in the Antarctic Peninsula. Then, in February and March 2002, it fell apart. Scientists observed the collapse through satellite imagery, watching in near real time as the shelf fractured into thousands of icebergs and disappeared. The trigger was surface melting. Warmer summer temperatures created meltwater on the ice shelf's surface. The water flowed into crevasses, widening them through a process called hydrofracture, water freezing in cracks and expanding, wedging the ice apart. Once enough crevasses formed, the shelf lost structural integrity and shattered catastrophically. The entire process, from the first major fracturing to complete disintegration, took about 6 weeks. The consequences were immediate. Glaciers that had been feeding into Larsen B accelerated dramatically once the shelf was gone, some flowing up to 8 times faster than before. Without the shelf's restraining force, ice flowed freely from land into the ocean, beginning to contribute to sea level rise in ways it hadn't when the shelf existed. The acceleration continued for years, only gradually slowing as the glaciers adjusted to their new, shelf-free configuration. Larsen B's collapse was a preview. It demonstrated that ice shelves we assumed were stable can disappear rapidly under warming conditions. It showed that the threshold between stability and collapse can be narrow. A few degrees of warming, a few summers with excessive surface melt, and systems that persisted for millennia can vanish in weeks. Other ice shelves around Antarctica are showing similar warning signs: surface melting, crevasse formation, thinning. Larsen B wasn't unique. It was first, but it might not be last. Antarctica's role in carbon storage extends beyond ice. The Southern Ocean around it absorbs significant atmospheric CO2. Cold water holds more dissolved gases, making the Antarctic Ocean a crucial carbon sink that helps moderate climate change. The ocean absorbs about 25–30% of human CO2 emissions annually, and the Southern Ocean around Antarctica accounts for a disproportionate share of that uptake, despite covering only about 20% of the ocean's surface. The mechanism is straightforward. CO2 dissolves more readily in cold water than warm water. Antarctic ocean temperatures near or below zero create conditions where the water can hold far more dissolved CO2 than tropical oceans. Additionally, the Southern Ocean experiences intense biological productivity during summer. Phytoplankton blooms consume CO2 through photosynthesis, converting it to organic matter that eventually sinks to the deep ocean, sequestering carbon for centuries or longer. But the carbon sink is changing. As the Southern Ocean warms, its capacity to absorb CO2 decreases. Warmer water holds less gas. Changes in circulation affect how much deep water upwells and mixes with surface water, influencing CO2 exchange rates. And ocean acidification, the consequence of absorbing too much CO2, is affecting marine ecosystems in ways we're only beginning to understand. The Southern Ocean is already more acidic than it was a century ago, with pH dropping measurably. This affects organisms that build shells or skeletons from calcium carbonate. Pteropods, certain plankton species, corals. More acidic water makes it harder for them to build and maintain these structures. If key species decline, it could affect the entire Antarctic food web, potentially reducing the ocean's biological carbon sequestration capacity. Antarctica's ocean is performing a service for the planet, absorbing carbon pollution we're generating, slowing the rate of atmospheric CO2 increase. But it's not infinite. The ocean can't absorb carbon indefinitely without consequences. Acidification, warming, circulation changes all affect its capacity. We're loading more and more carbon into a system that has limits, and Antarctica's ocean is showing signs that we're approaching or possibly exceeding those limits. Glaciers in Antarctica move at different speeds. Some flow just centimeters per year, while others race toward the sea at several meters per day. These ice rivers respond to hidden bedrock topography, ocean temperatures, and lubrication from meltwater we're only beginning to map. Understanding glacier flow is crucial for predicting future ice loss and sea level rise. Slow-moving glaciers are typically in cold, stable regions with shallow slopes. The ice deforms under its own weight, flowing like an extremely viscous fluid, creeping downhill at rates measured in centimeters or meters per year. Fast-moving glaciers, ice streams, can flow hundreds of meters per year or even several meters per day. These glaciers are often lubricated at their base by meltwater or till, sediment that acts like ball bearings between ice and bedrock. Pine Island Glacier and Thwaites Glacier in West Antarctica are among the fastest flowing and most concerning. They're losing mass rapidly, thinning, accelerating as they flow toward the ocean. Satellite measurements show their flow speeds increasing over time, suggesting they're destabilizing. The bedrock beneath them slopes downward inland, exactly the configuration that makes marine ice sheets vulnerable to irreversible retreat. What's fascinating and concerning is how quickly glacier behavior can change. A glacier flowing steadily at one speed can accelerate or decelerate in response to changing conditions. Remove an ice shelf that was buttressing it, and the glacier speeds up within weeks or months. Increase ocean temperatures, melting the glacier from below, and flow accelerates. Add meltwater at the base, lubricating the bed, and flow speeds up further. These glaciers are dynamic systems, constantly adjusting to conditions, and small changes can have large effects. We're mapping them in increasing detail. Satellite radar interferometry can measure ice velocity with meter-scale resolution, revealing the complex patterns of fast and slow flow, showing where glaciers are stable and where they're changing. But prediction remains difficult because the systems are complex, the process is incompletely understood, and the future conditions they'll experience uncertain. The Antarctic Treaty prohibits mining and mineral exploitation, preserving the continent's resources indefinitely. This protection was extended in 1991 for at least 50 years, but questions remain about what happens when that period expires. Antarctica contains mineral resources, coal, iron ore, possibly oil and natural gas in offshore regions, rare earth elements, perhaps more we haven't discovered. The mining ban protects these resources, but it's not permanent. The original Antarctic Treaty, signed in 1959, focused on demilitarization and scientific cooperation, but didn't explicitly address mineral exploitation. As interest in potential Antarctic resources grew during the 1970s and 1980s, treaty parties negotiated additional protocols. The result was the Protocol on Environmental Protection to the Antarctic Treaty, signed in Madrid in 1991, which designated Antarctica as a natural reserve devoted to peace and science, and banned all mineral resource activities except for scientific research. The ban is comprehensive: no mining, no oil drilling, no commercial exploitation of mineral resources. It's enforced through consensus among treaty parties, all of whom must agree to any changes. Modifying or ending the ban would require unanimous agreement, giving each party effective veto power. This makes the ban relatively robust, but not absolute. The question is what happens in 2048 when the protocol becomes open to modification. Will countries uphold the ban, or will resource scarcity and economic pressures lead to calls for exploitation? Antarctic resources are largely theoretical at this point. We don't know how much is there, how accessible it would be, whether extraction would be economically viable. But as resources become scarcer elsewhere and technology improves, the calculus might change. For now, Antarctica remains protected, its resources preserved for future generations, or perhaps preserved permanently as a conscious choice to leave some places unexploited. It's a remarkable achievement, this international agreement to forbid commercial activity on an entire continent. Whether it survives beyond July 48 depends on decisions we haven't made yet, on values we'll hold decades from now, on whether we'll choose continued preservation or eventual exploitation. Ice loss in Antarctica has tripled since 2012, according to satellite measurements tracking the continent's mass balance. What was once a gradual process is accelerating in ways that challenge our predictions about future sea levels. The data is stark. Antarctica lost around 76 billion tons of ice per year between 1992 and 2001, 148 billion tons per year between 2002 and 2011, and 219 billion tons per year between 2012 and 2017. The trend is toward faster loss, not stability. The acceleration is concentrated in West Antarctica and the Antarctic Peninsula. East Antarctica remains close to balanced, with some regions possibly gaining ice from increased snowfall. But West Antarctic glaciers are thinning rapidly, their grounding lines retreating, their contribution to sea level rise growing year by year. The ice shelves buttressing these glaciers are thinning from below as warm ocean water melts them, reducing their stabilizing effect. What concerns scientists most is the acceleration itself. If ice loss was steady, we could predict future sea level rise with reasonable confidence. But accelerating loss means our predictions keep needing revision upward. Models from a decade ago underestimated Antarctic contribution to sea level rise because they didn't account for processes we've since observed: ice cliff instability, hydrofracture, rapid grounding line retreat. Each new understanding reveals mechanisms that could accelerate ice loss further. The implications are profound. Current sea level rise is around 3 and 4 millimeters per year, split roughly between thermal expansion of warming oceans, melting mountain glaciers, Greenland ice loss, and Antarctic ice loss. If Antarctic contribution doubles or triples, entirely possible given current acceleration, sea level rise could reach 5 to 7 millimeters per year or more. That adds up quickly. An extra few millimeters per year over decades means tens of centimeters of additional rise, substantially worsening coastal flooding and storm surge impacts. We're in a period of transition, watching Antarctica shift from near stability to net loss to accelerating loss. The question is whether this acceleration continues, potentially triggering rapid collapse of vulnerable ice sheet regions, or whether it moderates, allowing more gradual adjustment. We don't know yet. The ice will tell us through measurements we make year by year, watching the continent transform in response to a warming world. The grounding line, where glaciers lift off bedrock and begin floating, is retreating inland in many parts of West Antarctica. This retreat can trigger unstoppable ice loss, like pulling a cork from a bottle as ice flows more freely once it's no longer anchored. The grounding line is the critical boundary where glaciers transition from grounded ice, moving slowly over bedrock, to floating ice shelves, moving faster as they're no longer held by friction with the ground beneath. When the grounding line retreats, several things happen simultaneously. The glacier loses contact with bedrock over a wider area, reducing resistance to flow. Ice that was grounded becomes floating, subject to ocean currents and tides that flex and stress it. And perhaps most importantly, if the bedrock slopes downward inland, as it does beneath much of West Antarctica, retreat exposes thicker ice to ocean water, increasing the rate of melting and potentially triggering further retreat. This creates a positive feedback loop. Retreat leads to faster flow, which thins the ice, which causes more retreat. The process can become self-sustaining, continuing even if the conditions that triggered it stabilize or improve. Scientists call this marine ice sheet instability, and it's one of the most concerning mechanisms for rapid ice loss. Once started, it might not stop until the ice sheet reaches new equilibrium, potentially hundreds of kilometers inland, representing meters of sea level rise. Satellite measurements show grounding lines retreating in several critical West Antarctic glaciers. Thwaites Glacier's grounding line has retreated 14 kilometers since the 1990s in some areas. Pine Island Glacier shows similar patterns. The retreat isn't uniform. It happens in pulses, with rapid retreat followed by temporary stabilization, then more rapid retreat. The pattern suggests that bedrock topography influences the process, with ridges temporarily slowing retreat before it continues across deeper basins. What makes this particularly concerning is the irreversibility. Even if we stopped ocean warming tomorrow, grounding lines that have retreated into unstable configurations might continue retreating. The ice sheet could be committed to substantial loss even if we halt further climate change. It's like pushing a ball over the top of a hill. Once it starts rolling downward, stopping the push doesn't stop the ball. Antarctica might have similar inertia, processes we've set in motion that will continue regardless of future actions. Antarctica's contribution to sea level rise has accelerated from essentially zero in the 1990s to about 0.6 millimeters per year now. While this sounds small, the acceleration is what matters. Each decade brings faster changes than the one before. In the early 1990s, Antarctica was close to balanced, gaining roughly as much ice from snowfall as it lost from ice discharge to the ocean. By the 2010s, it was contributing about as much to sea level rise as Greenland, and the rate continues to increase. To understand why 0.6 millimeters per year matters, consider cumulative effects and acceleration. If that rate stayed constant, it would add 6 centimeters by 2100, significant but manageable. But if acceleration continues at current rates, Antarctic contribution could reach several millimeters per year by mid-century, adding 30-40 centimeters or more by 2100. And if marine ice sheet instability triggers rapid collapse, the numbers could be much higher. Sea level rise isn't uniform globally. It varies by location due to ocean currents, gravitational effects, and land subsidence. Some regions experience more rise than the global average, but Antarctic ice loss contributes to global mean sea level, affecting coastlines worldwide. Every additional millimeter of rise increases flood risk, storm surge impacts, coastal erosion, and saltwater intrusion into freshwater systems. The acceleration is visible in the data. Plot Antarctic ice mass over time, and the curve bends downward, steepening as you move toward the present. This isn't natural variability. It's a trend driven by warming ocean water reaching Antarctic ice shelves, by atmospheric warming increasing surface melt on the Antarctic peninsula, by processes we've triggered that are now operating at increasing rates. Perhaps most sobering is the realization that we're still early in this process. Antarctica contains enough ice to raise sea levels by about 60 meters if it all melted, Even if only a fraction melts, even if East Antarctica remains stable and only West Antarctica contributes significantly, we're talking about meters of sea level rise over coming centuries. The 0.6 millimeters per year we're seeing now is the beginning, the initial acceleration of a process that could continue for decades or centuries, fundamentally reshaping coastlines worldwide. Melting Antarctic ice doesn't just add water to oceans. It changes ocean salinity, which affects currents and marine ecosystems. Fresher water from ice melt floats on denser salt water, disrupting circulation patterns that have remained stable for millennia. Ocean circulation depends critically on density differences. Cold, salty water sinks while warm, fresh water floats. These density-driven currents distribute heat, nutrients, and dissolved gases around the globe. Add large amounts of fresh water from melting ice, and you reduce surface salinity. Lower salinity means lower density, which weakens sinking that drives deep ocean circulation. The effect isn't uniform. Fresh water spreads unevenly, creating regions of lower salinity that can disrupt local circulation patterns. In the Southern Ocean, meltwater from Antarctic ice spreads along the coast and offshore, creating a lens of fresher water that sits atop the denser ocean beneath. This matters for Antarctic bottom water formation, the process where very cold, salty water sinks and flows north along the ocean floor. If surface water becomes too fresh, it won't sink as readily, weakening this critical component of global ocean circulation. Measurements already show changes. Antarctic bottom water is becoming warmer and fresher, and its formation rate appears to be declining. These are subtle changes so far, but they're consistent with predictions from climate models. Marine ecosystems respond to salinity changes in complex ways. Some species are sensitive to salinity variations, while others are tolerant. Changes in salinity can affect where species can survive, potentially shifting distributions and ecosystem composition. The Antarctic marine ecosystem evolved under relatively stable salinity conditions, and rapid changes could stress species that are already dealing with warming temperatures and changing sea ice patterns. The freshwater input from melting ice is accelerating. As more ice melts, more fresh water enters the ocean, potentially amplifying circulation disruptions. It's another feedback loop, another mechanism where ice loss creates conditions that could accelerate further changes. Antarctica isn't just losing ice, it's changing the ocean around it, with consequences that ripple through marine ecosystems and global circulation patterns. Some Antarctic species are shifting their ranges as temperatures change, moving southward to find suitable ice conditions. Emperor penguin colonies have disappeared from warming areas, appearing in new locations as they track the ice they depend on. This represents adaptation in real time, species responding to changing conditions by relocating, seeking environments that match their requirements. Emperor penguins are particularly sensitive because they breed on sea ice that must be stable from April through December. If ice forms too late or breaks up too early, the entire breeding cycle fails. Colonies at the northern edge of the species range are most vulnerable, experiencing more variable ice conditions as climate warms. Some colonies have declined dramatically or disappeared entirely, while new colonies have been discovered farther south, where ice conditions remain stable. Other species show similar patterns. Adelie penguins, which prefer colder conditions and rely on sea ice are declining in the warming Antarctic peninsula, but increasing in colder regions farther south. Gentoo and chinstrap penguins, which tolerate warmer conditions, are expanding their range southward. The Antarctic ecosystem is reorganizing geographically, with cold-adapted species retreating south and more temperate species advancing. The shifts reveal both resilience and vulnerability. Resilience because species can respond to changing conditions by moving, finding new habitats, adapting their ranges. Vulnerability because not all species can move, not all regions can support displaced populations, and the rate of change might exceed species' ability to adapt. Emperor penguins relocating to new ice is adaptation, but it's also a sign of stress, an indication that their traditional breeding grounds are becoming unsuitable. There's also a limit to how far south species can move. Antarctica is a finite continent. Species pushed south by warming will eventually run out of southern habitat. The continent ends at the pole. There's nowhere colder to retreat to. This creates a potential extinction risk for species that are true cold specialists, adapted to conditions that might not exist anywhere on Earth if warming continues beyond certain thresholds. The Antarctic ozone hole has begun to heal since the Montreal Protocol banned CFCs, showing that global cooperation can work. The hole is now smaller than in previous decades, offering hope that collective action can address atmospheric changes. Peak ozone depletion occurred around the year 2000, when the ozone hole covered over 28 million square kilometers, larger than North America. Since then, atmospheric CFC concentrations have declined, and ozone depletion has gradually decreased. The recovery is slow. CFCs are long-lived in the atmosphere. Some persist for 50-100 years or more. Even though we stopped producing them in the 1990s, the CFCs already in the atmosphere continue destroying ozone. Recovery to pre-1980 levels isn't expected until around 2070, roughly 80 years after the Montreal Protocol was signed. But the trend is positive, measurable, and consistent with scientific predictions. The Montreal Protocol is often cited as the most successful international environmental agreement ever implemented. It achieved near-universal participation. 197 countries are parties to it. It phased out ozone-depleting substances effectively, with production declining to near zero by the late 1990s. And it's working. The ozone layer is recovering, demonstrating that when the international community agrees on a problem and implements solutions, we can reverse atmospheric damage. But the ozone hole also serves as a warning. We came remarkably close to catastrophic damage. If CFC production had continued unchecked for another decade or two, ozone depletion might have spread beyond the poles, affecting mid-latitudes where most of the world's population lives. UV radiation levels could have increased globally, causing widespread health impacts and ecosystem damage. We avoided this outcome through relatively early action, but it was close, closer than most people realize. Antarctica's ozone hole recovering is a success story, a demonstration that we can address global atmospheric problems. It provides a template for addressing climate change, international cooperation, science-based targets, phased implementation, mechanisms for compliance and assistance. The challenges differ. Climate change is more complex than ozone depletion, involves more economic interests, requires deeper transformation of energy systems. But the ozone hole's recovery proves that success is possible when we choose to act collectively. We've mapped the surface of Mars in more detail than we've mapped the bedrock beneath Antarctica's ice. Satellite radar can penetrate ice, but the sheer thickness and remote location mean vast regions remain essentially unknown to science. We can see the ice surface clearly through satellite imagery, but the bedrock beneath, the actual solid continent, is mapped at much lower resolution, with large areas where data is sparse or absent. Ice-penetrating radar provides the primary method for mapping subglacial bedrock. Aircraft fly over Antarctica carrying radar instruments that send radio waves through the ice. The waves reflect off the bedrock and return to the receiver, allowing measurement of ice thickness and bedrock elevation. But Antarctica is enormous, and comprehensive coverage requires flying millions of kilometers of survey lines, a task that's still incomplete despite decades of effort. Recent projects have filled in gaps. The Bed Machine Antarctica project, completed in 2019, provided the most detailed bedrock map to date, incorporating decades of radar data from multiple international teams. The map revealed features never seen before: subglacial mountain ranges, valleys deeper than the Grand Canyon, lakes, river channels, all hidden beneath kilometers of ice. But even this comprehensive effort has limitations. Some regions remain poorly surveyed, bedrock elevations uncertain by hundreds of meters. Why does bedrock topography matter? Because it controls ice flow, determines glacier stability, influences where subglacial lakes form, affects how the ice sheet responds to warming. A valley in the bedrock might channel ice flow, accelerating glacier movement. A ridge might stabilize a grounding line, slowing retreat. Deep basins might contain warm ocean water that melts ice from below. Understanding bedrock topography is essential for predicting future ice behavior. The fact that we know Mars better than Antarctic bedrock is both humbling and motivating. Humbling because it reveals how much about our own planet remains unknown, how vast the gaps in our knowledge are even for something as basic as what the land looks like beneath the ice. Motivating because it highlights opportunities. Every radar survey flight adds to knowledge. Every new mapping project reveals hidden features. Every improvement in understanding helps us predict how Antarctica will respond to climate change. The possibility of life in Antarctica's subglacial lakes raises profound questions about life's tenacity and the nature of isolation. If organisms evolved separately there for millions of years, they might represent a second genesis of life, independent of Earth's surface biosphere. This isn't merely extremophile microbes surviving in harsh conditions. It's potentially an entire ecosystem, cut off from surface life for so long that it evolved separately, creating life forms found nowhere else on Earth. The conditions in subglacial lakes are extreme by surface standards, but potentially stable enough to support life. They're dark, no photosynthesis possible. They're cold, temperatures near or slightly above freezing. They're isolated, no exchange with surface ecosystems for potentially millions of years. They're nutrient poor, limited organic matter, limited chemical energy sources. Yet despite all this, they might host life. Lake Whillans, sampled in 2013, contained diverse microbial communities, not just one or two species barely clinging to existence, but hundreds of bacterial species forming a functioning ecosystem. They were chemosynthetic, metabolizing minerals and dissolved chemicals rather than relying on organic matter or sunlight. The lake wasn't sterile, it was alive, actively cycling nutrients, supporting complex microbial interactions. If Lake Whillans hosts life, probably dozens of other subglacial lakes do too. And if some have been isolated for millions of years, like Lake Vostok, sealed for at least 15 million years, the organisms there might be significantly divergent from surface life. Not a separate origin, they almost certainly descend from microbes that existed before isolation, but potentially evolved in directions unavailable to surface organisms, developing unique adaptations, metabolisms, possibly even genomic features not found elsewhere. The implications extend beyond Earth. If life exists in Antarctic subglacial lakes, it strengthens the case for life on icy moons, Europa, Enceladus, perhaps others. These worlds have subsurface oceans beneath ice shells, conditions potentially similar to Antarctic subglacial lakes. If life can thrive in Earth's subglacial environment, it could thrive there too. Antarctica becomes an analog, a place where we study what life might be like in similar environments elsewhere in the solar system, preparing for missions that might one day sample those distant oceans. Antarctica is a natural archive of human history, preserving everything from ancient atmospheric composition to industrial age pollution. Ice cores contain traces of Roman lead smelting, medieval volcanic eruptions, and the beginning of fossil fuel use. Earth's memory in frozen form. Every major event that affected the atmosphere shows up somewhere in Antarctic ice, recorded with precision and waiting to be read. Lead pollution from Roman silver mining appears in ice cores dated to around 2,000 years ago. The Romans didn't reach Antarctica, they probably didn't know it existed, but the lead from their smelting operations entered the atmosphere, circulated globally, and fell as snow on the Antarctic ice sheet, where it remains preserved. We can measure the exact amount, track how it varied over time, see the rise and fall of Roman industry reflected in lead concentrations in ice. Volcanic eruptions leave clear signals. The 1815 Tambora eruption, one of the most powerful in recorded history, deposited sulfate across Antarctic ice that we can detect and measure today. The 1883 Krakatoa eruption, the 1991 Pinatubo eruption, all of them visible in ice cores, their atmospheric impact preserved in chemical layers. We can even detect eruptions that weren't directly observed, finding volcanic signatures in ice, and then searching historical records for corresponding events. The Industrial Revolution is unmistakable. Carbon dioxide concentrations in ice core bubbles show the dramatic rise beginning around 1800, accelerating through the 20th century. Lead from leaded gasoline peaks in the mid-20th century, then declines after regulations phased it out. Radioactive isotopes from nuclear weapons testing appear in ice from the 1950s and 1960s. Every human impact on the atmosphere, from local pollution to global greenhouse gas emissions, is recorded in Antarctic ice. This archive is irreplaceable. If Antarctica melts, these records are lost. Ice cores represent the only direct atmospheric samples from the past. Everything else is indirect inference from proxies. The ice holds actual ancient air, actual atmospheric dust, actual chemical signatures from events thousands of years ago. It's Earth's memory, its record of atmospheric conditions and events, preserved because Antarctica is cold enough and stable enough to maintain ice that's hundreds of thousands of years old. Protecting that archive is protecting our ability to understand Earth's history and predict its future. The continent's extreme isolation creates a thought experiment. If Antarctica were as temperate as Europe, would civilization have developed there independently? Its geographic isolation might have prevented outside contact for millennia, potentially creating radically different cultures or technologies. Antarctica is farther from other continents than any other major landmass. Separated by the Southern Ocean's fierce waters, unconnected by land bridges, invisible from any other shore. If Antarctica had been temperate during the Holocene, the past 12,000 years when human civilization developed, and if humans had somehow reached it, they would have been almost completely isolated. The nearest lands, the southern tip of South America, New Zealand, Australia, are thousands of kilometers away across some of Earth's stormiest seas. Without advanced navigation, Antarctic populations would have been cut off, unable to trade, share technology, or interact with other human societies. This isolation might have led to unique cultural evolution. Technologies developed elsewhere, agriculture based on Middle Eastern grains, metalworking techniques from various centers, writing systems from Mesopotamia or China might never have reached Antarctica. Populations there would need to develop everything independently, potentially following completely different trajectories. Perhaps they'd domesticate different species, develop different social structures, invent different technologies based on Antarctica's resources. Or perhaps isolation would limit development. Human progress often comes from cultural exchange, from ideas spreading between societies, from competition and cooperation between groups. Complete isolation might mean slower innovation, fewer resources to draw on, smaller population unable to support specialization. Antarctica's hypothetical civilization might remain in a developmental stage that other regions passed through millennia ago. It's pure speculation, of course. Antarctica wasn't temperate during the Holocene. Humans never established permanent civilization there. But the thought experiment reveals something about geography's role in history. Civilization didn't develop uniformly. It arose in specific places, spread through specific routes, shaped by specific geographic realities. Antarctica's isolation reminds us that geography matters profoundly, that where you are on Earth influences what becomes possible culturally and technologically. Antarctica reminds us that Earth still holds vast mysteries, landscapes barely explored, ecosystems barely understood, processes that could reshape our future. In an age when we think we've mapped everything, this frozen continent preserves wonder, inviting contemplation of all we have yet to discover. We've explored less than 1% of Antarctica on foot. We've sampled a handful of subglacial lakes out of hundreds. We've mapped the bedrock incompletely, understood the ice sheet partially, begun to grasp how critical the continent is to global climate. Every year brings new discoveries, new species found in deep Antarctic waters, new subglacial lakes detected through radar surveys, new understanding of ice dynamics from satellite measurements, new climate records from deeper ice cores. Antarctica yields its secrets slowly, demanding effort and patience, rewarding persistence with revelations that change how we understand our planet. The mysteries aren't just scientific, they're existential. How much warming can Antarctic ice withstand before collapse becomes inevitable? What life exists in subglacial lakes, and what can it teach us about biology's possibilities? How will changes in Antarctica affect the rest of Earth? And how quickly will those effects manifest? These aren't questions we can answer definitively yet. We have hypotheses, models, estimates, but not certainty. Antarctica keeps its secrets, revealing them gradually as we develop tools and understanding to decipher them. There's something valuable in this uncertainty, this acknowledgement of how much remains unknown. It keeps us humble, prevents the arrogance of thinking we understand everything. Antarctica is vast, complex, and responds to forces operating at scales from molecular to planetary. Understanding it requires patience, requires willingness to accept incomplete knowledge, requires comfort with mystery that might not resolve quickly. The continent teaches that exploration isn't finished, that knowledge isn't complete, that Earth still holds places where humans are visitors rather than residents, where nature operates on its own terms, largely independent of our presence. In our increasingly crowded, mapped, understood world, Antarctica remains fundamentally wild, fundamentally mysterious, fundamentally beyond complete human control or comprehension. That's worth preserving, not just the ice, not just the ecosystems, but the mystery itself, the reminder that some things remain unknown, some places remain beyond our full understanding. Scientists who spend time on Antarctica's ice shelves describe sounds unlike anything else on Earth. Deep groans, sharp cracks, eerie singing as ice shifts and breaks. The ice is never truly silent. It speaks in a language of stress and movement, of forces too vast for human scale. When ice bends, it creaks. When it breaks, it thunders. When wind resonates through crevasses, it produces tones that range from bass rumbles to high, haunting whistles. Ice shelves floating on the ocean rise and fall with tides, flexing with each cycle. This flexing creates stress that builds and releases, and the release is audible. Cracks propagating through ice, fractures opening, segments shifting relative to each other. Researchers camping on ice shelves report being startled awake by sudden loud cracks, sounds like gunshots or thunder, coming from the ice beneath their tents as fractures form or expand. The sounds reveal processes invisible to the eye. Ice flowing over bedrock bumps produces sustained vibrations, ice quakes, detectable with seismometers. Icebergs calving from glaciers create roars that carry for kilometers, audible long before the ice hits the water. Even the settling and compaction of snow produces faint crackling, a kind of whisper from the accumulating ice sheet. Some researchers describe the ice's sounds as musical, almost intentional, as if the continent is singing. Wind through ice creates resonances, organ pipe effects where cavities in the ice produce specific pitches. The combination of multiple sources, cracks, groans, wind tones, ice settling, creates complex soundscapes that vary with weather, season, and location. Antarctica has an acoustic character, a sonic identity that's uniquely its own. Listening to ice isn't just aesthetic, it's scientific. Acoustic monitoring helps detect calving events, track iceberg movement, study glacier dynamics. The sounds ice makes reveal stress patterns, fracture propagation, flow characteristics. Antarctica speaks in these sounds, telling anyone who listens about the forces shaping it, the stresses building within it, the changes happening too slowly to see but fast enough to hear. Antarctica operates on timescales that dwarf human perception, ice that's millions of years old, landscapes that change over millennia, processes that unfold across centuries. Living in proximity to such deep time changes perspective, makes human concerns seem brief and urgent things against a backdrop of patient, inexorable change. The ice sheet has existed for over 30 million years in some form, growing and shrinking with climate cycles, but persisting through the entire span of time when the first apes evolved into humans. A single ice core spanning 800,000 years contains more time than modern humans have existed as a species. The ice at the bottom fell as snow before our ancestors diverged from other hominins, before tool use, before language, before almost anything we'd recognize as distinctively human. It's been ice, continuously, through the entire human story, and hundreds of thousands of years before that. This deep time is difficult to conceptualize. Our lives span decades. Our civilizations span centuries or millennia at most. Antarctica's ice spans hundreds of millennia. Its bedrock has been roughly where it is for hundreds of millions of years. The continent has existed in recognizable form for far longer than that. The ice sheet flows at meters per year, a pace that means a journey from interior to coast takes thousands of years. A snowflake falling on the East Antarctic Plateau today might reach the ocean 100,000 years from now, having flowed through ice that will encase it for longer than our species has existed. Yet we're changing Antarctica on human timescales. Ice that accumulated over hundreds of thousands of years is melting in decades. Systems stable for millennia are destabilizing within a human lifetime. We've compressed the timescale of change, forcing processes that should take tens of thousands of years to occur in mere centuries. It's a collision of timescales. Antarctica's patient, slow processes meeting humanity's rapid, transformative impact. Standing on Antarctic ice, knowing you're walking on snow that fell before recorded history, changes how you think about time. Your footprints in that snow are momentary, erased by the next wind. But the ice beneath will outlast everything you know, flowing slowly toward the ocean, preserving the atmosphere you breathed in tiny bubbles that will exist for millennia after you're gone. Antarctica teaches humility about time, about the brevity of human existence against the duration of geological processes, about how quickly we can change things that took eons to build. From Antarctica's interior, the ice extends to every horizon, unbroken white stretching to infinity, an experience of space that's both liberating and terrifying. There are no landmarks, no features to orient by, just ice and sky meeting at a distance that could be kilometers or tens of kilometers. Depth perception fails on featureless white plains. The horizon becomes abstract, theoretical, a line where white meets blue without texture or reference. This emptiness affects perception. Distance becomes meaningless when there's nothing to measure it against. A person walking toward you might be 100 meters away or a kilometer. You can't tell until they're much closer. Small irregularities in the ice surface can look like mountains when they're actually just ridges a few meters high. The mind, desperate for scale and reference, invents features that aren't there, sees patterns in randomness. Travelers in Antarctica's interior describe the experience as otherworldly. You're surrounded by more of the same in every direction. White ice, blue sky, nothing else. No trees breaking the horizon, no buildings, no rocks, no variation except subtle changes in the ice surface texture. It's monotony on a scale that becomes almost hallucinatory, an environment so uniform that the brain starts filling in details that don't exist. Yet there's also freedom in it. Nothing constrains movement except your endurance and supplies. You can walk in any direction, and the landscape won't change. It's ice regardless of where you go. There's something liberating about that uniformity, that lack of imposed direction. No paths to follow, no obvious destinations, just space opening in all directions equally. The ice horizon represents Antarctica's essential character: vast, uniform, indifferent to human presence. We cross it briefly, leaving tracks that disappear, occupying space that cares nothing for our occupation. The ice was here before us, will be here after us, stretching to every horizon, patient and immense and utterly itself. Antarctica embodies a paradox, seemingly permanent yet surprisingly fragile, ancient yet vulnerable to rapid change. The continent appears eternal, unchanging ice stretching across a frozen landscape, yet measurements show it transforming within decades, responding to warming with a speed that defies its apparent solidity. How can something so massive, so old, so cold, change so quickly? The answer lies in thresholds and feedbacks. Ice sheets appear stable until they're not, sitting near equilibrium points that can shift rapidly when conditions change sufficiently. Small warmings can trigger large responses. A little ocean warming melts ice shelves, which removes buttressing, which accelerates glaciers, which delivers more ice to the ocean, which raises sea levels and changes ocean circulation. The system has amplifiers built in, mechanisms that make small changes grow larger. This makes Antarctica simultaneously robust and fragile. Robust because it survived natural climate variations for millions of years, persisting through warm periods and cold periods, adapting to changing conditions while maintaining its essential character. Fragile because we're pushing it beyond natural variability, applying forcing faster than it can adapt to, potentially triggering changes that become self-sustaining and irreversible. The paradox extends to timescales. The ice sheet's current configuration took millions of years to establish. It's ancient, stable in that sense. But it can destabilize in centuries or even decades if pushed hard enough. Permanence and fragility coexist, the former a product of deep time and stable conditions, the latter a consequence of rapid forcing and systemic feedbacks. Understanding this paradox is essential for managing our relationship with Antarctica. We can't treat it as permanent, unchanging, infinitely tolerant of disturbance, but we also can't treat it as immediately collapsing, doomed regardless of action. It's vulnerable but not yet broken, changing but not yet collapsed, stressed but still functioning. What happens next depends on choices we make, how much we warm the planet, how quickly we act to reduce emissions, how seriously we take the warnings Antarctica is giving us through accelerating ice loss and changing dynamics. We are the first generation to understand Antarctica's role in climate, and the last generation that can prevent catastrophic changes. This responsibility sits heavily on a single span of human lifetimes. Our choices in coming decades determine outcomes for millennia. The ice sheet's stability, the Southern Ocean's circulation, the Antarctic ecosystem's survival, all respond to actions we take or fail to take in this narrow window of time. Previous generations didn't know. They couldn't measure ice sheet mass balance, didn't understand marine ice sheet instability, lacked the tools to see Antarctica changing. They acted in ignorance, emitting greenhouse gases without understanding consequences, assuming the ice was permanent, believing the planet could absorb whatever we emitted without fundamental change. We can't claim that ignorance. We know what's happening, why it's happening, what it means. Future generations won't have choices we have. If we trigger West Antarctic ice sheet collapse, they can't reverse it. It will unfold over centuries regardless of what they do. If we allow enough warming to destabilize East Antarctica, they inherit a commitment to meters of sea level rise that will reshape coastlines for thousands of years. The decisions we make constrain their options, determine the world they inherit, lock in consequences they'll live with long after we're gone. This creates an ethical weight unlike anything previous generations faced. We're making choices with millennial consequences, deciding planetary futures based on immediate considerations: economics, politics, convenience, ideology. The ice doesn't care about quarterly earnings or election cycles. It responds to physics, to heat accumulation, to thresholds crossed. Once triggered, ice sheet collapse operates on its own timeline, indifferent to human regrets. The responsibility is both collective and individual. Collectively, societies must reduce emissions, transition energy systems, protect Antarctic ecosystems, support research that improves understanding. Individually, we make choices about consumption, support political action, educate others, acknowledge the weight of living in this pivotal moment. Antarctica won't judge us. It will simply respond to what we do, melting if we warm it, stabilizing if we don't. The judgment will come from future generations, who'll know whether we rose to this responsibility or failed it. Antarctica represents Earth's last true wilderness, the only continent where nature still operates largely independent of human control. We visit, we study, but we don't dominate. We can't. The environment is too hostile, too vast, too fundamentally indifferent to human presence. This makes Antarctica precious in ways beyond its scientific or climate value. It reminds us that not everything is for us. Not everything exists to serve human purposes. No permanent human population has ever existed in Antarctica. Everyone there is transient. Researchers rotating through seasons or years, support staff maintaining stations, tourists visiting briefly and leaving. Nobody is from Antarctica in the way people are from other continents. Nobody has ancestral ties to the land. No indigenous cultures evolved there. No human languages describe it in words shaped by generations of living with it. It's humanity's one continental blank, the place we observe from outside rather than inhabit from within. This outsider status matters. We can't reshape Antarctica to suit us without destroying what makes it valuable. We can't warm it without melting the ice that defines it. We can't populate it permanently without confronting an environment that tolerates human presence only within narrow technological bubbles. Antarctica sets the terms, and we either meet them or leave. The Antarctic Treaty recognizes this implicitly. By dedicating the continent to peace and science, by prohibiting military activity and mineral exploitation, by requiring environmental protection, the treaty acknowledges that Antarctica should remain wild, should continue existing on its own terms, rather than being transformed into human space. It's an unusual recognition in a world where humans have modified nearly every other environment. There's value in having one place remain beyond our dominion, a place where we're visitors, where human rules and concerns matter far less than ice dynamics and katabatic winds and seal populations. A place that teaches humility, that reminds us of our scale relative to planetary processes, that exists as wilderness, not because we've preserved it, but because we haven't yet destroyed it. Antarctica is the last wilderness, not as achievement, but as warning. This is how little wild Earth remains when we don't constrain ourselves. Perhaps the most profound thing Antarctica teaches is the value of silence. Not just acoustic silence, but stillness, space, the absence of constant human noise and activity. In our hyper-connected, constantly stimulated world, Antarctica offers something increasingly rare: the opportunity to experience genuine quiet, to hear nothing but wind and ice and your own thoughts. This isn't merely pleasant, it's psychologically and spiritually significant. The silence forces attention inward. Without distractions, without stimulation, the mind quiets or becomes loudly aware of itself. Thoughts that would be drowned out by normal life's noise become audible. Anxieties, hopes, questions you'd normally avoid confronting rise to consciousness in the quiet. Some people find this uncomfortable initially. The silence feels oppressive, exposing. Others find it liberating, a release from constant input and demand. Extended time in Antarctic silence changes people. Researchers describe returning to civilization and finding normal noise levels overwhelming. Conversations too loud, cities too chaotic. The recalibration happens quickly. Within weeks or months of Antarctic experience, your baseline for quiet shifts. You notice sounds you'd previously filtered out, become sensitive to noise pollution in ways you weren't before. But there's also sound in Antarctica, just different sound, natural rather than human. Wind variations, ice creaks, distant seabirds at coastal stations. These sounds exist in silence rather than competing with it, punctuating quiet rather than destroying it. They become meditative, markers of time and condition, reminders that silence isn't absence, but a different kind of presence. The experience of Antarctic silence is increasingly valuable as genuine quiet becomes rarer globally. Noise pollution affects most human habitation. Even remote areas have aircraft overhead, distant highways, electrical hums. Antarctica offers escape from that, a place where silence exists not as pause between sounds, but as the fundamental condition occasionally interrupted by natural events. It's a gift the continent offers, this quiet, and like many Antarctic gifts, we don't appreciate it fully until we've experienced it and lost it again. Antarctica asks nothing of us. It doesn't need saving in the sense that it would die without our help. The continent existed long before humans, will exist long after, regardless of what we do. But what might die is the Antarctica we know, the configuration of ice and climate that has persisted through human history, the frozen continent that regulates planetary climate and harbors unique ecosystems. That Antarctica is vulnerable to our choices, and saving it means saving ourselves from consequences of its transformation. The continent will survive warming. It's survived warmer periods before, existing with less ice or different ice distribution. Life will adapt or relocate. Antarctic species have survived climate variations for millions of years. The physical continent, the bedrock and mountains and valleys beneath the ice, won't disappear. What we risk losing is the current state, the stable ice sheet, the ecosystem configuration, the climate regulation that Antarctica currently provides. This reframing matters. We're not saving Antarctica for Antarctica's sake. We're preserving the climate stability that Antarctic ice provides for our sake. We're protecting the ecosystems that exist now, not because they're the only ecosystems Antarctica could support, but because they're adapted to current conditions and valuable in their current form. We're preventing sea level rise that would inundate our cities, not Antarctic cities. Antarctica has none. Antarctica asks us to understand consequences, to recognize that the continent's transformation affects us far more than it affects Antarctica itself. The ice sheet can melt and reform over geological time. We can't rebuild coastal cities as easily. The ecosystems can evolve and adapt over millennia. Human civilization can't wait that long for stability to return. What Antarctica asks ultimately is whether we're wise enough to preserve stability that benefits us, whether we can act on knowledge that clearly shows consequences, whether we value long-term sustainability over short-term convenience. The continent doesn't plead or demand, it simply exists, responding to physical laws, changing or stabilizing based on conditions we control. The asking is our own, the question we pose to ourselves. What kind of world do we want, and are we willing to act accordingly? If we choose to preserve Antarctica, to stabilize climate and protect the ice, we give future generations a gift beyond measure: a stable climate, protected coastlines, and a continent that remains wild and mysterious. The ice contains climate history, supports unique ecosystems, regulates planetary temperature, offers scientific insights available nowhere else. Preserving it means maintaining all these functions for centuries or millennia to come. The gift isn't just practical, stable sea levels, functioning climate regulation, though those matter immensely. It's also cultural and spiritual. Future generations would have the opportunity we've had to wonder at Antarctica's vastness, to study its mysteries, to stand on ancient ice and feel the weight of deep time. They'd have a wilderness to contrast with their settled world, a place that remains fundamentally wild, fundamentally beyond human dominion. Conversely, failing to preserve Antarctica's ice means bequeathing catastrophe: rising seas, disrupted climate, lost ecosystems, a transformed planet that future generations must cope with. They'd inherit our failure, live with consequences of choices they didn't make, watch coastlines retreat and cities flood because we couldn't or wouldn't act when action mattered. The choice seems stark when framed this way, yet it's the choice we're making, consciously or unconsciously, through actions and inactions taken today. Every year of delayed climate action is a year of additional warming, additional ice loss, additional commitment to future sea level rise. Every year of effective action is a year of reduced forcing, slowed ice loss, protected stability. Antarctica's gift to us has been stability, a frozen continent that helped regulate climate through the entire span of human civilization, providing conditions that allowed agriculture, cities, the development of everything we recognize as modern life. Our gift to future generations could be preserving that stability, maintaining the climate conditions that made our own flourishing possible. Or our legacy could be transformation and loss, a melted Antarctica and all the consequences that follow. We choose, through what we do in the years immediately ahead, which gift we give. Antarctica invites contemplation of time, of scale, of human place in natural systems, of what we value and why. The continent exists as teacher, offering lessons in patience, resilience, fragility, consequences. It asks us to think beyond ourselves, beyond our immediate concerns, to consider planetary time and planetary space, to acknowledge forces larger than human control, and changes we can nevertheless influence. This is the final lesson, perhaps the most important one. Antarctica shows us both our insignificance and our power, holding the paradox that we're tiny against geological time, yet capable of transforming planetary systems. We're small, individual humans barely registering against Antarctica's vastness. Our lives brief flickers against the ice's duration, our concerns ephemeral compared to the patient flow of ice sheets. Yet collectively we're powerful enough to destabilize those ice sheets, to trigger changes that will persist for thousands of years, to transform a continent through activities occurring thousands of kilometers away. We're simultaneously insignificant and world-changing, powerless and powerful, observers and agents of transformation. Antarctica holds this paradox without resolution, presenting it for our contemplation. Stand on the ice and feel how small you are, how brief your life, how meaningless your concerns are to the continent flowing beneath your feet. Then remember that you and billions like you are warming the planet, melting the ice, changing Antarctica in ways no natural process has done for millions of years. Both things are true. Neither negates the other. Perhaps this is Antarctica's deepest gift, this invitation to hold contradictions, to be humble and responsible simultaneously, to acknowledge limits while accepting agency. The continent doesn't judge, doesn't moralize, doesn't demand. It simply exists, vast and patient and slowly changing, responding to physics without caring about politics or economics or human intentions. It's up to us to learn from it, to take the lessons it offers, to choose wisely while we still can. The ice waits, as it has waited for millions of years, as it might wait for millions more, or might vanish within centuries, depending entirely on choices we make in this narrow window of time. Antarctica invites us to choose carefully, to act wisely, to remember that some things, once lost, cannot be recovered on timescales that matter to human civilization. The invitation is extended. How we respond determines not just Antarctica's future, but our own. And so we've traveled together through 100 facts about Antarctica, from its basic dimensions to its profound mysteries, from the ice's silence to the questions it poses about our future. We've crossed ancient forests preserved in coal, walked past ghost mountains buried beneath kilometers of ice, listened to the continent speak in groans and cracks, considered what it means that the ice sheet is changing within our lifetimes. Antarctica exists now as it has for millions of years, vast, cold, patient, indifferent to human concerns yet profoundly connected to human fate. The ice that regulates our climate, that holds memories of atmospheres past, that might reshape our coastlines in the future. All of it sits there at the bottom of the world, flowing slowly toward the ocean, waiting to see what we do next. Perhaps you're drifting now, thoughts mixing with dreams, the ice and wind and silence of Antarctica blending with whatever peace you found tonight. That's good. Let the continent's patient rhythms slow your own. Let the deep time it represents put your concerns in perspective. Let the cold and quiet offer rest. Sleep well, knowing that while we've explored these 100 facts, Antarctica itself remains mostly unexplored, mostly mysterious, mostly patient. The ice will be there tomorrow, flowing as it has for eons, indifferent to whether we wake or sleep, whether we act or remain still, whether we rise to the responsibility of this moment or let it pass. The bottom of the world waits, frozen and timeless, holding its secrets in ice, inviting wonder, teaching patience, reminding us that some things matter on scales beyond our own, that some places exist for themselves rather than for us, that the earth is vast and mysterious and worthy of our care. Rest now. Let Antarctica's silence be your silence, its stillness your stillness, its ancient ice a reminder that time moves slowly for those patient enough to wait. Good night.